This is week 12 or I think 12 or 11. This one this week. I didn't remember what is the week number now. I think 12 is it or 11? Anybody? Please confirm me by message or something. Okay, later. Okay, record has started. Okay. Okay, I think everything is fine now. Okay. So this topic, you can see some picture here. Smart control. Okay, smart control, smart irrigation control. Okay, so this one I will explain in the last class. I will show you some explanation how actually this thing. Okay. All right. So today actually, but before this, you need to know how to how to get the understanding all of this thing. Okay. Okay. So maybe we can continue from the before. Okay. Okay. Can you see the slide emitter types? I wish slide is moving now. Can see the slide? Emitter types.
Yes,
Can
sir.
we? Okay. So please respond quick because sometimes if you don't respond, I feel that maybe the connection or something is a problem. All right. And sometimes if it is not clear or hang or not moving, please give him stop me. Okay. Okay, you can see this is the one of the important is the emitter, is it? Because microirrigation, as I mentioned before, that system that we showed you before that. Okay, like this one. Okay, or maybe if we see our layout. Okay, this is the layout, is it? Layout. So layout, you're clear now. So it is a source. Source is water, means palm. To the field is the crop, and the emitter is located. You can see the circle. This circle actually is the emitter. Okay, so emitter is actually connected with the lateral. Okay, so this is the lateral. All right. So emitter is the last component, last device. So emitter, what is the purpose of emitter? Emitter actually the water water delivering device. Okay, or water emission device. Okay, because emitter is very small, so that's why sometimes called emission, sometimes called discharge. Okay, so emitter we have a different types. Okay, so this is the some cross section. If you see this emitter, it is a looks round, but if you open it, you can see this is some cross section like this. Okay, so meaning that water flows like this. Okay, all right. So this what happened actually, water flows like zigzag like this. It meaning that it doesn't flow straight. When water flows straight, the velocity will be high. Okay, but here what happening, when water flows, it hit on this corner, then water flows, it hit on the corner, meaning that like if we run or if we walk very fast, let's say in front of someone, so then meaning that our speed is reduced or stopped suddenly. Okay, so here happening the same thing. So water moving and hit to this wall, the velocity becomes maybe zero, then again start. Okay, same thing happening. So this way, so velocity is reduced, pressure is also reduced. Okay, okay, so actually this is the inside the emitters. You can see here some groove. Okay, so just showing here is if it is open it. Okay, because this is circular. If you cut it and then if you make it straight, it looks like this. So we have a different types of emitters. Okay, many types of emitters. Okay, so whatever this is, this look as different shape. This is a different shape, but from the technical side, we have only two types. Okay, all right. So this one actually I forgot to show you something, but I will show you maybe if it is not available in the slide, maybe next session I will show you. Okay. So this is the emitter type. So another one. This is this as I mentioned. There is another type. One emitter is like this, like this. Okay. And then this is the pipe. So we can install manually like this. You can see here manually. Okay. So those emitters is outside like this. Okay. So meaning that this is manually installed. Okay. And another type, this is like this. We cannot see, but emitter is inside the pipe. Okay, so this is called inbuilt. Okay, inbuilt. All right, like this. Okay, maybe you can see here. Okay, actually inbuilt like means this. So this is the emitter. So it is inside the pipe. Okay, so this is the opening. So when you install on the field, so water discharge by drop. Okay, so this is called inbuilt. Okay, so this one we can get by pipe. Okay. So anyway, both way we can, but this is called uh, on point. On point means it is separate. Means you have to buy the emitter separate. Then you have to this is called online actually. Okay, inline and online. It looks almost similar thing. Inline means the emitter is what called already built in the pipe. So meaning that pipe and emitter comes together. This is called inline. Okay. And online means emitter is separate, pipe is separate. You can buy it separately, then you can manually you can fix it. Okay, these two types. We have many types. Okay, and as I mentioned, you can use it flat, sloping, terraced, any type of soil. Okay, I mentioned before. Okay, so this is very important thing. Okay, you can see here we have a many thousand, maybe more than 1,000 models of emitters we have in the market by different companies, but there are two categories. One is called non-pressure compensating emitters. Another is called pressure compensating emitters. Okay, all right. So what does it mean actually? So meaning that let's say we have a pump here. We have a pump. Okay, so this pump is supplying water. Okay, and we have the emitter here. Let's say this is the lateral, this is the lateral, this is the lateral, and emitter is here. Let's say here is emitter, here is emitter, here is emitter, here is emitter, here is emitter. Okay, this is the emitter. So previously I discussed that the pump we have a different types of pump. Okay, because pump we can increase the flow by speed. Is it? If we increase the speed, the water flow rate will increase. Okay, similar like our car when we press on the accelerator, car speed is increased. So similar to pump, we have a like this. Pump is when we speed up. So Q means discharge. Okay, so discharge will increase. So when discharge increase, so meaning that pressure will increase. Pressure will increase. Okay. So I wish I explained before that every emitter has some specification. Okay. Every emitter has some specification. So that specification is at least when you buy any emitter, let's say this emitter. Okay. Where is this? Okay. Let's say this emitter. Okay. When we buy this emitter, so every emitter has some specification. What is the specification? So first one is the Q. Okay, what is the Q? Means flow rate. Okay, what is the flow rate? So let's say flow rate is saying 2 liter per hour. Okay, so meaning that if you use these emitters, if you run it, it will give you the water. If you run it, it will give you, this is the, okay, Q. Okay, sorry, I think I write nicely. Okay, one is the Q. Okay, so Q is 2, let's say 2 liter, or maybe 1 liter, maybe 1.5 liter. Okay, so unit is usually liter per hour, means that if you install this emitters, it will give you 2 liter water every hour. Okay, and last time I mentioned that normally the range is 1 to 8 liter per hour easily. Okay, but beside this there are some special emitters are available, maybe more than this, but very special, only bubbler type. Okay, but usually we use 1 to 8 liter per hour. Okay, so this is the Q. Another one is pressure. Pressure means operating pressure. That's why it is called ASP. AS means head. Okay, AS means head. You know the head. Head means the elevation. Okay, so meaning that, let's say it is 1 bar. Okay, 1 bar. Okay, okay, 1 bar. 1 bar means actually 10 meter. 10 meters. So what does it mean? When, let's say you buy the emitter, this emitter you buy, and in the catalog it was written that Q 2 liter per hour, ASP 1 bar, meaning that 10 meter. What does it mean? Meaning that this emitter, when you run, let's say this emitter is connected with lateral, is it? Let's say emitter is connected here, connected here, connected here. So this is the lateral. So the last emitter here, last one, and this is the manifold. Okay, this is the manifold. So water is coming to lateral. So this is the manifold. So the last emitters, not only last, every emitters, but if last one is received, everyone will receive. Okay, so that's how we say last emitter. Okay, this one, but actually every emitter. Okay, because when water flows, at the beginning pressure is high, and when water moves to the end, pressure becomes low. This is normal, like water supply from the source to your house. Okay, so pressure slowly, okay, means gradually pressure is reduced. Okay, so what does it mean? So this thing you have to understand. So Q is 2 liter, meaning that once you install this emitter, so this emitter will give you 2 liter every hour. Okay, so this is your plant, so it will discharge here 2 liter water in 1 hour. Okay. Mm. Okay, second, ASP. This is very important one. ASP is 1 bar, means 10 meter. What does it mean? It means that when you install this emitter and you have a pump, okay, so you should have a right pump, so that pump can create pressure here. 1 bar. 1 bar means 10 meter. Okay, at this point. Okay, so you have to choose the right pump. So if you choose the small pump, so the pump will not be able to generate pressure 1 bar or 10 meter. What is 10 meter means? 10 meter means if you connect, let's say this is the emitter, this is the emitter. So instead of emitter, if you connect a pipeline here, like 10 meter or 11 meters, so the water can raise up to 10 meter. So this is the meaning of ASP 1 bar. So meaning that water will, but here there is no pipe. Instead of this, we use the emitter. So emitter will do. So that's why we have, this is the meaning. So meaning that uh, the pump must send minimum pressure here 10 minimum at the last one. So when we can send 10 meter pressure, then only we will get 2 liter per hour. If pressure is drop, so our Q will drop also. Like you can see sometimes in your house when you open the tap, if pressure is good pressure, so water flows very nicely. But inside the pipe pressure is low. After opening the tap, you can see what happened. The water flow becomes very low. Is it? Am I right? So this is actually Q and SP. So simply when you buy the emitters, you must look at least these two. Simple answer is so meaning that this emitter needs operating pressure. So meaning that this emitter we have to operate with this pressure. When we can operate this pressure, this emitter will give you 2 liter. Okay, all right. So if we cannot operate with 1 bar, so meaning that emitter will work, but we will not get the 2 liter. So that is the answer. So how to achieve this one? We have to choose the right pump. Okay, we have to choose the right pump. So today I will show you the example. When you see the example, then you will know how to ensure that our emitter has right emitter will receive the right pressure. Okay, so this is the things you have to understand. And when you buy any emitters, this at least these two you have to look it. Another one you have to look. So that one is diameter, weighted diameter. Okay, so it will show another one is called weighted diameter. Weighted diameters, maybe DW. It will say that okay, when you run this emitter for different soil. So it will give you different soil. Let's say clay soil, sandy soil, this soil, different soil. It will give you okay, clay soil. Let's say it is, let's say 10 centimeter. Okay, maybe sandy soil is 6 centimeter. Some information will be given because the manufacturers company they tested in the field. After testing, they found the data. So that data they express in the catalog. All right. So this is the thing. Okay. Okay, so this at least these three. One is Q, another is pressure. This pressure means actually we call operating pressure. Okay, operating operating pressure. What is the operating pressure of the emitters? Okay, operating pressure. All right, operating pressure. So this is the emitter needed. Okay, this is called operating pressure. Emitter needs this pressure. Okay, unless so this three information at least required. Okay, so now we can see here. So sometimes although you buy the new, although you collect the right emitters, sometimes the pressure can increase or decrease depending on the slope. Okay, like you can look when you drive car low to high or high to low. Okay, or maybe let's say sloping land. Okay, let's say land is like this. So if you drop water from here, so water will go very fast, meaning that pressure will increase. Okay, one is velocity will increase, pressure will increase because due to the elevation. Elevation is high because this is the elevation, because I already explained in the hydraulics the topic. That's why I explained hydraulics. What is the energy? Okay, so actually this pressure that I mentioned here, ASP. Okay, so this is the actually energy. So any energy, as I explained before, three components is it? One is the elevation, another is the depth of water, another is the velocity. Three components. Okay, so due to the flat sloping terrace land, okay, sometimes pressure can increase and decrease. Okay, so when water moves high to low means downward slope, so pressure is increase means gain, pressure gain. Okay, pressure gain. But when water moves like low to high like this, upward slope, so pressure is drop. Okay, so pressure is decreases. So due to that, what happened? So we have a pump, and let's say my field is here and land is like up and down like this, okay, whatever. So when reach here, or maybe your land is here, okay, like upward, this one is downward. So when downward, you will gain the pressure. So meaning that, let's see, your pump here is, if pump give here 10 pressure, so when it comes here, you will get more pressure. But if you go upward, the pressure will drop gradually. Okay, so that's why at the end we have to ensure that emitter receive the right pressure. Okay, right pressure. So this is very important. Okay. Okay, so from the design calculation you can understand today, hopefully. So that's why we have a two types of emitters. One is called non-pressure compensating emitters. Another is called pressure compensating emitters. Pressure, you can see here, pressure compensating, this one. Okay, what is the difference? Difference, I think you can see from the graph. Is it? Can you see? Last slide I showed you that every emitter you have a few characters. One is Q, another is what? Operating pressure, ASP. Okay, sometimes some books it is written like this, AC. AC means, E means emitter, AC is head. Okay, head. AC is, we call AC means head. Actually, head means height or energy. Okay, head. And E is emitter. Okay, E means emitter. Okay, E means emitter. All right. So now we can see this two figures. Okay, you can see here pressure. This one first we say non-pressure. So non-pressure emitters. So this is the field data. When you use non-pressure compensating emitters. So if we test in the field, you can see the data here. The x-axis is showing pressure. Pressure means that I showed 1 bar, 2 bar, 3 bars. Okay, like this. Okay. Here is a PSI. PSI is another. PSI is actually pound per square inch. Okay, PSI. PSI is pound per inch square. Okay. So pressure, we have a very different unit. Okay, meter, feet, kilopascal, pascal, bar, centibar, so many things we have. Okay. Okay, so I already showed you the units, different units you can convert. All right. Okay, so you can see x-axis pressure started from 10 here and it is 40, and y-axis it is a Q. Okay, so meaning that this is the pump. So pump means when you start pump, you Q increases, and the same time if we pressure increases, then you can see if pressure increases or maybe Q increases, what happening? You can see here. Let's say 10, 20, 30. So when pressure increasing, Q is increasing, or you can say when Q increasing, pressure is increasing. It is not constant. Okay, and I mentioned that before. The each emitter, you have a data specification. Specification means, let's say this emitter is 2 liter per hour. Okay, 2 liter per hour, and let's say this operating pressure is, let's say 20. So meaning that if we say 2, you can see here, this is the point, 20 and 2. This is the, sorry, pressure is pressure is 20 and Q is 2. 2 means actually here, this point. Okay, this point. All right. So we can have a many different type. So this one may be 2.5. Okay, it's showing 2.5. 2.5. Let's say for 20 it is 2.5. Okay, but you can see if pressure is increases, discharge is also increases. Okay, if pressure increases, discharge. If pressure decreases, discharge also decreases. So meaning that if we have these emitters, it needs minimum pressure 20. So when you have minimum pressure this 20, then only you can get 2.5. If you come less than 20, you can see, let's say 20 to 15. If you come middle here, then if you go up, then your discharge is no more 2.5. It is less than 2.5. So meaning that discharge is reduced. Okay, so this is called non-compensating pressure, non-pressure or non-compensating emitters, meaning that when pressure increases, discharge will be unstable. Discharge also will drop or increase. Okay, it is not constant. But if you look this one, pressure compensating, you can see at certain pressure, it's here or maybe here. Even you increase the pressure, the discharge is constant. Discharge will not change. All right, meaning that you increase the pump pressure, pressure is increasing, but discharge is constant, meaning that at the same rate, like 2 or 2.5, it is same rate. Okay, same rate. But if it is the pressure is minimum, pressure is less than this one, this means operating pressure means you need minimum pressure. So when it's a minimum, so you can see if pressure is not sufficient, then discharge will drop. But once, this is called critical or minimum pressure. Okay, so once your pressure is minimum pressure or more than minimum pressure, or it is called permissible or critical pressure, so meaning that even pressure is increasing, you can see pressure is increasing but discharge doesn't increase. So this is called compensating pressure, compensating emitters. Okay, so this has a application you can, because the reason is, our land is not flat. Okay, as I mentioned, land is not flat. Okay, so sometimes our land is like up and down like this. Okay, so when water flows, the pressure will drop here, but then we have to increase the pressure. But when you use compensating this type of emitters, you will get the discharge everywhere same. Okay, pressure will increase, pressure will change. You can see here pressure is changing, but Q will not change. Okay, but this one, with changing the pressure, Q is changing. You can see continuously changing, continuously changing. Okay, so that's why this emitter is, it is not suitable when your land is undulating or sloping land. So this emitter is not suitable. What will happen? Because if with pressure discharge is increasing, so meaning that, let's say it is set Q, it set Q equals 2 liter. But if it is increasing, so meaning that Q will be more, maybe 4 or 3. So meaning that your crop will be over irrigated. Your crop will be over irrigated or maybe will be underwater. So crop production will not be nice. But this one, you can maintain the constant discharge. So clear this one. So this decision you have to actually, when you do for design calculation, you have to choose which type of emitter is suitable. Okay, sometimes maybe when you do the design calculation, you cannot you cannot solve the problem with this, then you have to go for compensate this type. Okay, so only difference is this type is very stable, operating is very stable. Okay, but this one is unstable. Okay, but in terms of cost, this is very cheap, this is expensive. Okay, because it has some mechanisms. The emitter has some mechanism inside. Okay, all right. So this is the two types of. Okay, okay. Another important criteria is when we develop the microirrigation system. Okay, we maintain the efficiency like 90%, or we call variation is 10%. What does it means? It meaning that let's say this is the manifold. You know the manifold now, is it? And manifold connect with the lateral. Okay, the lateral. All right. So now we have a emitter here, is it? We have to install emitter every, let's say 1 meter or 2 meters. We have many emitters. Okay. And now let's say this emitter have a Q. This emitter have a Q is 2 liter per hour. Okay. I just explain you what does it mean, 90% or 10%. So now we bought the emitters, that emitters installed and running in the field. So we start the system. So water is applying in the field. So we have to do some test. Okay. So by testing, we have to confirm that the difference, let's say you had 20 meters, 20, let's say 20 meters. So these 20 meters, you just run for 10 minutes or maybe 5 minutes or maybe one hour. It's okay, no problem. Okay. You collect the water in the glass. Glass means like a paper cup is okay. You just collect the water because once you start, so the water will drop, is it? Like this, water will drop here. Okay, water will drop. So you collect in the glass or flask. Then you measure it. How much water is every cup? Volume of water. Okay. Then you can get volume of water each cup. So this difference among these emitters, among this cup, it should be 10%. Okay, 10% means, let's say if we run for 1 hour, if we run 1 hour, so normally if we run 1 hour, you can see the ditches Q means 2 liter per hour. So meaning that if we run 1 hour, if we put here cup, okay, and if you run the 1 hour, so meaning that we will get 2 liter of water if we run 1 hour. Okay, so as a standard and optimum or perfect, every cup will receive 2 liter of water if we run for 1 hour. So this is the meaning of Q. Okay, but it is very uh, impossible. We will not receive like this. There will be some variation. So this variation will be 10%. You can see this variation will be 10%, or efficiency will be 90%. It is the same, meaning that 100 minus 90. So if 90% is accuracy, so 10% is variation. So what is the 10% variation means? Actually, we should receive 2, but maybe you can receive here 2.1. Maybe here you receive 1.95. Okay, it can be plus minus, but not more than 10%. Okay, more than 10% means what? If we say 2 liter, 2 liter, 2 liter, 10% is how much? Zero point 0.2 is it? Zero point 0.2, zero point 0.2 liter. Okay, so meaning that maximum can be 0.2 liter, it means 2.2 liter. Here can be 1.8 liter. So within this range, okay, it should not be more than this. So this is the criteria. So meaning that after designing, after developing, we must fulfill this criteria. One is the application uniformity, that is called 90%. Otherwise, we can say variation 10% is the same thing, but we explain different way. All right. Okay. So this is the things. Okay. And this is the emitter ditches. Okay. As I mentioned that every emitter when it ditches the water, the Q is like this. K is the constant, X is the power also. It is called emitter pressure discharge component. Okay, and P is the pressure. So sometimes we can also write K H X. So unit is here is maybe this one is PSI or kilopascal, but H here is in meter. H means meter. Okay, so it is the same thing. Okay, okay. So just now told you the compensating emitters and non-compensating emitters. What is the difference? You can see here written here. Okay, exponent classification of non-pressure compensating emitters. X is 1. Okay, all right, and ODPs or here is called compensating is 0.5. Okay, you can see the next slide. It can be easily understand. Okay, you can see here. Okay, what is this X? X is the power of the this formula, is it? This one. This is the X. So this is the emitters formula, emitters equation. Okay, emitters equation. Okay, so meaning that Q equals K is X. Now you can see if X is increasing, you can see this one. And when X is 0.5, it is like this. When X is less than 0.5, it is more stable. Okay, okay, but when X is more than 0.5, you can see the curve. So it is non-compensating. All right. So meaning that if you see the exponential, so this one is X is more than 0.5 and here X is less than or equal to 0.5. This is compensating. Okay, so this is the characteristics of the emitters. Okay, so meaning that all the non-compensating emitters, the Q equals K is X is maybe 0.6. If it is 0.6, so meaning that it is not this one, not this one. It is not compensating. It is non-compensating because X is more than 0.5. So when X is more than 0.5, your emitter is not stable, meaning that when pressure is increases, discharge will change. But non-compensating, but pressure compensating emitters will not be like this. Pressure will increase, but discharge will be the same. Okay, so this is the characteristics of this. Okay, all right. So this is so many things. Okay, okay. So this one actually just one more thing I just tell you because just now I told you that uh, this is the equation. Okay, Q equals K H X. Okay, as okay. What? Yes, I give some details just to understand what is the emitter, because if you don't understand this one in the field, you cannot solve the problem. Okay, you cannot identify what is the problem, what is the things is going on. Okay, so that's why I just I just explain a little bit more about the emitters. Okay. Okay, so this one meaning that let's say you buy the emitters. When you buy the emitters, okay, so these emitters will give you some specification of some data. All right, maybe you'll say, okay, this emitter Q, okay, Q is it's a 2 liter, okay, or maybe 1.5 liter, any discharge, no problem. Okay, for 1 hour, mean that if you run 1 hour, it will give you 2 liter. So now what you buy? Let's say you buy the 10 emitters. Okay, you buy the 10 emitters, then connect with the pipeline. Let's say this is your house wall. In the house you have the water supply, so you have connect with the tap, then supply the water and connect the one pipe. Okay, then you put the some paper cup or something or flask, then you collect water, run for 1 hour, then see how much water is each cup. Okay, collect it. Once you collect, this is the data like this. Okay, you can get the Q like 1.6, 1.4. Okay, all right. So if you have a let's say if you run with the different pressure, then you can find like ditches like this. You can see when pressure is 35, ditches like this. When 70, ditches like this. This mean, what does it mean? This means this is non-compensating emitters, meaning that X is more than 0.5. Okay, because according to the two types, when pressure increases, discharge will not change. This is called compensating, but this is discharge changing, mean X is more than 0.5. Okay, simply you can understand. So this is the data. Then you can see, uh, okay, this way you can test the data also. After this, you can see the small example here. Okay, where is this? Uh, where is this? Here, this is the different example. Okay, so this example 5.12, it is, it should be, it should be the non-compensating. Okay, so determine the emitted discharge coefficient and exponential regression analysis using the equation 5.3 and 5.31. This is the theory and this is the theory one. Okay, so then you can plot it here. Then you can, once you plot it, then you can derive this equation with the p. Okay, so meaning that using this equation, you can, this equation actually like this, q k h x. Okay, so meaning that this 0.26 is the k. Okay, actually if you put in the Excel, it is very easy. So k is 0.26, 0.216, and x equals, you can see 0.446. 0.446 means this is a compensating emitters, this one. Okay, so once, and then if you find the slope between 2 points, then you can find the k. Okay, so this is the information is given. So this way you can actually test whether this information is correct or not. All right. Okay, so this one actually I think everyone knows how to find the slope. Okay, because this one, this k is the slope, actually slope of this line. So if we take the 2 points, you can see here log, this is the log scale. Okay, so if we take the 2 points, so it is a, the y2 minus y1, x2 minus x1. Okay, I think this one, so using this we can find this. Okay, find this find the x and what called the slope. Okay, x we can find because x is actually this formula. You can see the equation 5.3, x equals log q1 by q2 and pressure. So you just choose any 2 point. Okay, from here. Okay, when you plot it, or maybe you can take the data from here also. You can take this data, you can take this, because let's say this is the P1, so this is the Q1, this is the P2, this is the Q2. So here you can see P1, P2, Q1, Q2. So when you put it, you can get the X. Okay. So once you get the X, then you can find this KE equals QE by PEX. Okay. All right. So means any value you can find the KE, because this X is already calculated. Okay, so meaning that if you take, let's say, this one, you can see the formula QE. Q means here is 1.44, and P is PEX, meaning that it is 70. Okay, so 70 and 1.44, and X this one. Okay, clear or not this one? Maybe I just shortcut, I tell you. Okay, briefly I explain you how you can find it. Okay, sometimes you need to know, because this is the emitter equation. It is called emitter equation. Let's say you have a lateral emitter is here. Now you need to know, okay, what is the discharge for this emitter? Okay, you know the pressure. Okay, so the equation is this one, K is X. Okay, so you run the system, then you can get the data like this. Okay, P, Q. But when you want to know this P and Q, you need some pressure gauge. That is a device, pressure gauge. You need that device. Okay, so this device will give you what is this P, what is this Q. Okay, all right. So you have to set up the pressure gauge. Okay, pressure gauge, and Q you can find. Okay, you can collect the water. All right. Then what you have to do, you just, if you have this data, you just take any two datas, either this one or maybe this one. So when you get this one, this what you have, you can see here P and Q. If you set two data, so meaning that you get the P1, you get the P2. Okay, and then you get the Q1, you get the Q2. Once you have the P1, P2, Q1, Q2, you can find the X. This is the way you can use by equation. Another way, you can plot them, and then you choose any 2 points. Let's say here and here. When you choose it, so from here you can get like this. From here you can get like this. From here, so you can get this is called P1. This is P2. Here is Q1. Here is Q2. So from the graph also you can get P1, P2, Q1, Q2. Okay, otherwise table. So once you get this, then you use this equation. Use this equation either from here or from here. So put this data in this equation, then you can find the X. Okay, you find the X. Once you find the X like this, then you come to this equation. So K equals, okay, K equals what? K equals Q by H(x), is it? Q by H(x). Okay, so now let's say you bought the emitters. Now you have tested the emitters. So when you bought the emitters, let's say your emitters was, when you bought it, it was 2 liter per hour. But when you tested in the field, it seems that it is 1.95. Okay, so now you put Q equals 1.95 here, this one. Okay, then what was the pressure? So that pressure you can find from the uh, pressure gauge, like this table. Okay, so let's say 1.95. So here is no 1.15. Let's say 1.75. So it is 1.75. The okay, Q is 2.2. If we say 1.95, maybe in between somewhere here. Okay, so you can put it here. You can put it here. X is already calculated. Then you can find the K value of this emitters. Okay, all right. So this is the way you can find the constant. So once you find the constant and X exactly, then you can find actually theoretically, okay, what would be the emitter ditches. Okay, immediate discharge. So this is the main purpose. But when you buy from the market, maybe when you run in the practically, it will not be the same. It will have some variation. Okay, so that's how you have to, sometimes you need to calibrate. But anyway, what I mentioned, your variation should not be more than 10%. 10%. You know what is mentioned mean 10 month means 10%. Let's say if you have a field like this, okay, let's say you have a emitter like this. Let's say here is emitter, here is emitter, here is emitter. Okay, so meaning that if you supply one, so everyone should receive one, but it will not happen. So if we say one, what is the 10%? It is 0.1. So if 0.1, so meaning that it should be 0.9, 0.9 to 1.1 within this range. Okay, it should not be 0.89. Okay, so 0.9 to 1.1. Let's say here is 1.1, here is 1, here is 1.5, 1.9. So this is good. It should not be 0.7, 0.8. So meaning that once this, so this one will increase. When this one increase, your efficiency will increase. Sorry, efficiency will decrease. All right. So this is the purpose. Okay, so yeah, this is the different types of emitters as I mentioned. The pressure compensating emitters is normally X is less than 0.5. Okay, and there is another type is called fully turbulent. Turbulent means very abnormal. Speed is always changing. Okay, and here is okay, non-compensating when X is more than this. Okay, okay, so that's all I think I should go for. Okay. Okay, maybe if you want to move, that's why, because your syllabus is not actually very wide, so that's why I have given the slides. So if you watch my slides, you can find more details. Okay, all of this, I think you can find it. Okay, okay, this is the filter. Okay, now I will go for one example. Okay, try to understand what is this, how to develop the system. Okay, I'm not sure the example is this slide or other slide. Okay. I think other slide is scheduling. Okay, so some information we need I have already put here in the slide, different types of crop. Okay, last class I explained this one, is it already? Okay, so this one also I already explained how to find the water water content for the plant. Okay, so this one is, do you have any questions for this? Actually, I told you the water requirement we can determine different ways. Is it? One is this. This one means that climate, crop, and soil. Is it? All is included here. Okay, here. This one. This is the wetting percentage. This is the crop because root depth, and this is the soil. Okay, and this one is the management. Okay, so and the climate is later we include the climate. So this is the climate. Okay, T. T is ET actually here. Okay, so meaning that here we have a crop. This is the crop. This one is the soil. This is the decision management, and this is a climate ET. Okay, so everything is here. Okay, another is the just climate based ET based. Okay, just for ET. Okay, So that's why you can see that simply I just want to explain you. Actually, first step when you do the design or develop the micro irrigation system or sprinkler irrigation system, the first step is, yeah, you have to do the site visit, look the area, how is this, collect the data, what type of crops, what type of soil, what type of environment. So this is the basic data we have to collect as far as this information that I explained. Okay, but calculation, actually first step is start by crop water requirement. Okay, crop water requirement. Okay, so meaning that I just give you just one example here, then you can understand how to find the crop water requirement. Okay, let's say you're growing the strawberry. Okay, strawberry crop. So strawberry crop you're growing on a field. So it is zero point 0.3 meter by 1 meter. So meaning that this is the field, let's say. Okay, so this one, let's say I just draw 3. So when say 0.3 meter, 1 meter, so normally uh, sometimes it is mentioned plant to plant or row to row. Okay, so 1 meter means in this case is lateral. Okay, okay, lateral distance means one lateral to another lateral. So let's say this is the lateral. So this distance is 1 meter. So this is 1 meter. Okay, and 0.3 means you have a strawberry plant. So strawberry plant, one plant to another plant. This is the distance. So this is called 0.3. Okay, then so this is your plant information, means how plant will be or crop will be grown. Okay, or maybe how crop will be planted. So this is the layout 0.31. Okay, second need. Okay, what is your soil type? You must need the soil type. Okay, because what, from the soil type we need some information. Either we use or not, but we need some information from the soil. What is this? One is called field capacity, another is called permanent wilting point. Okay, and also available water. Okay, so meaning that if we know this field capacity and permanent wilting point, actually minus, if we subtract this one, we can get the, okay, we can get the available water. Field capacity minus permanent wilting point is available water. Okay, so but information is given in the table. Previously I showed you in my deep crop water requirement lecture. So means soil information is needed. Okay, then what is the plant water requirement? So the first step is you have to determine how much water required for this plant, is plant. Okay, so now micro irrigation system. In micro irrigation system, you have to find water for each crop. Okay, there are two ways actually. One is water, means we call LPD. You know the LPD I explained before, liter per plant per day. Another one is liter, okay, means volume of water per meter. Okay, so let's say you have a lateral like this. So every 1 meter, how much water you need? Okay, so actually if you can find the LPD, you can find this one. This one you can see here. Now let's say table in slide 10. I'm not sure it is 10 slide is correct or not. Okay, from here you can find the what means available water, means when your soil is sandy soil, the available water is 120. Okay, effective root gen strawberry you can find from the table, maybe this table it is given. Okay, all right, maybe the slide number can change because I didn't change here. Okay, okay, it's maybe not the same. Okay, but anyway the table is available. Okay, so once soil is given, you can find from the table. Okay, these two information. All right. Then you can see the next. Okay. Then MAD is 40%. Let's say you assume MAD is 40%, but there is some recommendation is given. Just now I showed you here this table. Okay, this slide. Okay, you can see the MAD. So different types of crop. You can see crop, shallow rooted crop, high value fruit crops. So MAD is normally within this range. If orchard like lemon, then some like fruits, okay, berries, this one is 40 to 50. But this is a grass or something deep rooted, it is 50. Deep rooted trees, maize, this one is 0.65. So this is a general recommendation. Okay, but if you change your management, you can change this thing. But general recommendation is this. Okay, this is a good. Okay, if you know this one, let's say your crop is vegetables. So you can say now, if my crop is vegetables, so meaning that my MAD is would should be 25 to 30, 40, like this range is better. If not, then you have to change the management. Okay. So this is the thing. So that's why I said from this, I can say, okay, let's say this is 40%. Okay. Then one is 40%, then we can calculate the S. Okay. S. So S is given the previous slide. Actually, this formula S equals available water, root zone depth, and MAD. So you can calculate the S. Okay. Once you have a S, okay, then you can find the this effective storage. Okay, this one. But in the last class, I told you because this data you don't have available. So in your case, this effective storage, you don't need to calculate. You can use maybe the one, or if you want to say, you can say, okay, 0.9 or 0.85. You can assume it if you use this equation. But if you say S equals to 1, so meaning that your LPD is ET, KC, and A. S is not available. Okay, that's 3. ETO, KC, A. So meaning that if you want to find the LPD, you need first ETO. Okay, now if I say what is the ETO, how you can get the ETO now? Let's say you want to grow the strawberry in your area. Okay, and the first step says that you have to find the what is the water requirement for one strawberry plant, LPD. Okay, so LPD and formula is ETO, KC, and this. Let's say S I consider 1. If S is equal to 1, so your formula is ETO, KC, and A. So how to find the ETO? Anyone? So can you listen me? Can you hear me or not? Hello? No sound. I said how we can get the ETO? Anyone? Did you understand my questions? I'm not sure whether you are connected or not. No answer. Can you hear me or not?
Yes, doctor.
So why don't respond then? I think the everyone should be your camera should be on then. Otherwise difficult to understand. Okay. So when I ask something, please respond it, because you can see here LPD. When you calculate the LPD, you need the ETO. So meaning that you need to collect the weather station data that I explained before. Okay, in your local station. So you have to calculate the ETO using that FAO Penman mounted method. Okay. Once you calculate the ETO, then you can find this A. What is the A? A is the area that you can find from this. You can see here 0.3, this one. Okay, this is the A. Okay, okay. So then you can find the area. Okay, once you can calculate the area, then ET, then KC value is, there is a table. Okay, so you have to get the maximum one, because when you see the KCA table like this, I think given in another one, so it has given the three values. Okay, three values. The initial period, mid season, and the late season. So normally the mid season is high. Okay, it looks like this. Okay, so you have to take the this value normally. So then you can calculate the ETO. ETO you have to calculate. Then once you calculate, then finally you can go for this is the area 0.31. Then this is the requirement. LPD equals this 0.96 liter per plant per day. So meaning that each plant needs 0.96 liter every day. Okay. So this is the first thing you have to understand, that yeah, this is the crop, meaning that you have a lateral now. This is the lateral. Now you have a plant here, you have a plant here, you have a plant here, you have a plant here. So meaning that every day each plant need this amount of water. Okay. So now you have a system, microirrigation system. So you have to design the system so that you have to supply this amount of water every day. Now your operation is 0.96. So 0.96 liter per hour. So in the market now we have a different types of emitters. It started from one. It has two. So meaning that if you use 2 liter per hour, emitter is 2 liter per hour. So simply you can see, if 2 liter per hour, if you run the emitters for 30 minutes, you can receive 1 liter, because 2 liter half is 1 hour means 60 minutes. So if you run 30 minutes, you get 1. Is it? This is the normal understanding. So meaning that you have to run 30 minutes. If you run 30 minutes, you can. But if you use small emitters, that is 1 liter per hour. If you run 1 hour, it will give you 1. But you need 0.96. In that case, you have to adjust the time. So maybe you don't need to run the 60 minutes, maybe 58 minutes. If you run 58 minutes, then yeah, it will this is some understanding. So this is the way we can understand. Okay. All right. Now you can see it was a plant to plant distance was 0.3. If plant to plant distance is 0.3, so how many plant you can grow in 1 meter? 1 meter. It is 3, is it? 1, 2, 3. Okay. Let's say this 0.3, and here is some gap. Okay. Let's say 3 meter or maybe 4. Okay. So then you can, once you find this one, then meaning that is, let's say if 1 meter, if you have a 3, then what is the discharge? Sorry, you can see here, I told you here, this one. We have a two. One is LPD, another is liter per minute. So if you know the LPD per plant, so meaning that if you have a three plants in 1 meter, then you can calculate this one. If three plants in 1 meter, 3 multiplied by LPD. So meaning that in 1 meter, this amount of water you need. Okay. Why you need it this one? Because you know we have a emitters two types, is it? One is inline, another is online. Inline means emitter is built in the pipe, and this is a fixed. Fixed means less emitter is one emitter is here, another emitter is here. So the distance is maybe 0.5 1 meter. Okay. So then how much water you can discharge here? Okay. So this is your plant. 1, 2, 3. Okay. Okay. So normally if plant is very close, let's say point 2, point 3, then you have to find this. Okay. You have to find this means every meter how many, because plant to plant distance. So we have emitter also similar like this. We have emitter also 0.3 meter, 0.3 meter, 0.3 meter. Okay. Okay. So every meter how many meters? So we have to calculate. Based on the calculation, we have to find the emitters. Okay. All right. So that's how we need to calculate. Sometimes we need to calculate LPD. Sometimes we need to calculate liter per every meter. It's called liter per meter. Another one is called LPD. LPD, what is the LPD? Liter per plant per day. And this one is liter per meter. But it can be per day also, no problem. Means how much water you need to supply in 1 meter every day. Okay. Then management term. Okay. Because the calculation says previous 0.96, is it? So this 0.96, now it is your choice. You want to supply this 0.96 in one time or two times. Okay. So this decision is depends on the crop. Okay. If crop root is very small, it is good to supply water two times or three times. You just divide this amount, let's say 0.96, 50-50. Okay. So morning you can supply half, then afternoon maybe around 2 o'clock or 4 o'clock, 3 o'clock, you can supply another half. Okay. Another half. Okay. So meaning that instead of 1 hour, you can run 30 minutes, 30 minutes, two times. Morning 30 minutes, afternoon 30 minutes. Okay. Like 1 liter water, you need to drink 1 liter. Now you can drink 1 liter morning, one time. Otherwise, you can take 1 liter two times. You can take four times. So so what is the suitable or convenient for you? Okay. I think the same way we should not apply more water same time. Okay. If we apply water by defined time, it would be better for crop. Okay. All right. Especially for the shallow root. If root is like below 0.3, 0.3, but if root is very deep, no problem. You can apply more water. Okay. All right. Okay. Like this papaya and other crop. Sometimes you need more water. Okay. I think you can see the calculation after this. Okay, so this explanation I have given in my previous video. So if I explain all of this thing, I think I cannot finish it. Okay, so that's why I have given some previous video, but it is not organized same like how I'm talking. There is no edit. Okay, so just I give it to you because I don't share this one with others, just for students. Okay, all right. Okay, I think this one I look it here. Okay, this one is maximum pressure filter. Okay, I think this one I explained, but I forgot that I wanted to show you one more thing. what is the operating pressure. Okay, so this is the maximum pressure. So maximum pressure means if this is the discharge, this one is the discharge. So when you operate, the pressure should not be more than this. If pressure is more than this, Q will not be same. Okay, Q will change. Okay, okay. So this is the general layout of any uh, plot. Okay, so meaning that if you want to grow or if you want to use the micro irrigation system, uh, okay, so this is called manifold and this is the lateral. Okay, and you can see this one. This is a topography, means land elevation. Okay, your land is like this. Okay, this is the land elevation. So you can see here 20, 18, 16, 14. What did what do you understand from here? You can see there are few things, few information is available here. First thing is manifold. This is the manifold and this is the lateral. Okay, so this is the, you can see the height 20, 18, 16, 14. So meaning that land is this way is downward. This is called downward slope. Okay, downward slope. Okay, and manifold is okay. All right. So meaning that your, let's call uh, other way I can say that okay, like if it is slope like this, okay, slope like this. So meaning that your okay, this is the slope. So your manifold, your lateral should be, your manifold should be this direction. Okay, manifold should be this direction. Okay, this direction. Okay, along the slope and lateral with the 90 degree. Okay, like this. Okay, okay. The reason is because we know that when slope increasing or decreasing, so with the slope increasing decreasing, the pressure will change. Pressure will change. So that's why our purpose to keep the pressure, lateral pressure stable. Okay, because this is the lateral. Okay, let's say if my slope is like this, and if we provide lateral is along the slope like this, so what will happen? The here pressure will be less and here will be high. Okay, so that's why we provide the manifold like here, lateral will choose like this. So meaning that same elevation. So lateral will along the same elevation. Okay, if we can put the same elevation, then we can maintain the pressure here and here same because it is the same elevation. Because by elevation changing, pressure will change. Okay, so this thing, but if you go for other way, it's no problem. You can do it. So in that case, the compensating and non-compensating emitters. So if you use compensating emitters, no problem, because this elevation will not affect you. Either pressure increase or decrease, you will get the same teachers. Okay. All right. So this is the way, and you can see here. Okay. This one is lateral. Okay. So meaning that if we see this, if I draw this one, if we draw this one, so this is the manifold like this one. This is the manifold here, and then lateral is both side. This is both side is lateral. Okay, okay, this is lateral is connection. Okay, this is the lateral connection. Then along this is manifold. So this is the manifold. Okay, So this here manifold is underground. Okay, maybe 1 feet, 2 feet underground. So then that's why like this. This is the manifold pipe. Then it connect with, okay, like this. Okay, so here is a white cup. Okay, this white one. This one. So when you supply water here, the water comes to this pipe and go left and right. Okay, so this is your lateral. So this is, in this case is, this one is called one manifold. Okay, so because under one manifold, you have a left and right, you have a lateral. So this is a called manifold. Sometimes this one also called block. Okay, it's called block. Block means your area. So meaning that the area grown under one manifold is a block. Okay, all right. So let's say if you have a 1 hectare land, 1 hectare land. Okay, if you have a 1 hectare land, suppose let's say you have a 1 hectare land. This is 1 hectare, and if you just you have a one manifold, so meaning that your block size is 1 hectare. Okay, these are the things. Actually, this is the same thing that I showed. This is the drawing is like this. Okay. Okay, so okay, one more. This one maybe I will come later when I do the calculation. Okay, this is the pump. Yeah, I think last one is a pump. Okay. I think I opened the another slide. This would be better. I think here I have not given the very details. Okay. But I think I can start from here, then I will open later. Okay. Just yeah, this one. Because we have to stop by 30 minutes. So then I think we can start here. See this one, this design we call design calculation, or when you want to grow crop under micro irrigation system, how we will do it. Okay, how will do it. So look this problem. Maybe you can say design a drip irrigation system for citrus orchard, some lemon or something like this. And maybe you have a land 1 hectare, or you can have a 5 hectare, no problem. Okay, you can put it 5 hectare, 10 hectares. That's not a problem. Okay, so I put it 1 hectare, and the length area with the length and breadth means width is 100 meters. Is meaning that your land both side is 100 meter. This size is 100 meter. This size also 100 meter. Okay, this way also 100 meter. So meaning that 100 multiply 100 is 10,000 meter square. Okay, 10,000 meter square. So 10,000 meter square means the 1 hectare. All right. Okay. So actually the first example, it is easy to understand considering 1 hectare. It's okay because actually the in the field it will not be 1 hectare. Maybe here is 100. This side is maybe 120. No problem. So it is 100 multiplied by 120. So it will be 1,2,000 meter square. Okay. Meaning that 1.2 hectare. Okay. It can be like this. So I do what you want, but when you practice it, you can change it. Okay, instead of 1 hectare, you can choose, let's say 100. Here is 80, 100. Here is 120, 125. You can change it. Then everything will change. Okay, for your practice. Okay, now I show you the few step. Okay, if you understand this one, then what we discussed before, everything you need it. Okay, once you calculate this thing. Let's say step one. Okay, I start from here. Step one. I told you the step one is crop water requirement. first thing that you need to design calculation. For design calculation, you need to calculate the crop water requirement, meaning that how much water need this plant. Okay, this is the important thing. Then crop water requirement that I gave you the formula before. You can see here. Okay, what is this formula? This formula is it? This one. Okay. Okay, and I mentioned that for your case, you can say this S equals to 1. Okay. If you use S equal to 1, you are more safe because you can see if S equals to 0.9, the LPD will be less. But 1 means you are little bit more. Okay, means calculation will be 0.1% more. Okay, because if you multiply by zero point 0.9, the value will be less. So that's why it is a safe side. Okay, very accurate. But that information we don't have. So that's why I recommended you assume S equals to 1. So if we assume S equals to 1, okay, so this one no need. Okay, so this one is used 1, so it is no need. So LPD equals to very simple now. Okay, you can see the equation. What is this? Actually, the problem is this one. Okay, so details problem here given. Okay, this is the problem. Actually, it is mentioned here, but actual problem is here. You can see this problem. Just read, and this is the all the information. So this all the information you need to correct. Okay, like landslide, land slope, water source, soil texture. What is the clay sand? Okay, field capacity, wilting point. So this once you know the soil type, actually most of the things you can find. Then pan coefficient, crop coefficient, weighting fraction. Okay, weighting fraction means what? The PW. Okay, all right, PW. Okay, so weighting fraction is also sometimes needed. You know the weighting fraction, which one? Remember or not? Okay, I think if we go to formula, you can see. This, yeah, this one. Okay, this is weighting fraction, meaning that in the micro irrigation system, if we have a crop like this, we only irrigate this area, is it? This area. So we don't irrigate here. That's why we need to use weighting fraction. When micro irrigation system, very careful. Okay, you must use it because we don't supply water here. Okay, so this is called weighting fraction, right? Okay, so I wish that please, if you don't understand or maybe confusing, please ask me questions. So these are the information actually need. You can see all the information. It is not difficult. Okay, this land slope. So you can get from the topographic map. So survey department, if you find the topography like this 30, 40, then you can go to the land slope. Okay, let's say your land is here and here. Okay, what is the high slope and low slope? Okay, high and low. Okay, so these are the 2 points. You can find the distance and you can find the difference, then you can find the slope. Okay, all right. Yeah, then what type of crop? What is the water source? Is there water source or not? Either it is source is pond, river, or groundwater. Source of water you have to find. Okay, so soil texture, if it is not available, you can collect the sample and send to the lab. Then you can get this one. Then you can find the texture. Okay. Once you know the soil texture, you can find the field capacity and this, okay, from the table. Otherwise, you can do the lab test also. By laboratory experiment, you can find it. Similarly, you can find the bulk densities. So weighting fraction, that is you have to consider, but weighting fraction you have a recommendation. So normally ORSAT is 0.4, 4%. Okay, means not 100% area. Means if you have a 1 hectare land, 1 hectare land means you have to irrigate only zero point 0.4 and zero point 0.6 is dry. Okay, pan coefficient 0.7 or 0.75 always. Crop coefficient. This information we need it. Okay. Now, first step is crop water requirement. Okay, crop water requirement. Okay, maybe before I stop, I will try to finish these 2 or 3 steps. This is very important. Don't stuck. Okay, so use that formula ETO, KC, and area. Okay, so meaning that actually this crop water requirement means LPD. LPD means liter per plant per day. So this is actually crop water requirement. Okay, what is this? ETO. Previously, I showed you the slide. KC and multiply by area. Area. Area means area of weighted means this plant, this plant. Actually, there are two things. One is planting area. Okay, another is weighted area. So this one it is weighted area. Okay, another one is the planted area. Planted area means maybe you can say AP. Okay, planted area. So planted area, how to calculate? Planted area we calculate plant to plant distance, meaning that this is the plant, this is the plant to plant distance and row to row distance. So this is called AP. But AW is AW is AW is plant to plant distance AP multiplied by fraction with PW. Okay, means how many percentage? Maybe we will irrigate only 50%. So it is 0.5. That is called weighting fraction. Okay, here given weighting fraction 0.4 or maybe it is 0.5, can be 0.6. Okay, depending on this. Okay, if crop to crop distance is more, this value will be less. If crop distance to crop distance is smaller, this fraction will be higher. Okay, so this is the LPD. So now you can see ETO. Now, once you want to calculate this one, again, you know how to get the ETO now. If you don't have the ETO value, you have to collect all the temperature, relative humidity, those data. Then you calculate the ETO. All right. Then you can get this crop water requirement. Okay. And if you don't have the climate data, then second option is you do the pan evaporation. Okay. The experiment. Just you put the pan, then see how much water is removed every day. Okay, from this pan. So that is EP multiplied by KP. KP is always 0.75. Okay, but the KP value, as I mentioned before, KP value actually range is 0.7, 0.7 to 0.8. Okay, so you can use any value 0.7 to 0.8, but I always recommend to use in the middle 0.75. Okay, you can use 0.75, but in this problem it is given 0.7. That's why it is 0.7. Okay, and KC value is given, crop coefficient 0.8. If coefficient given, it is this, and this is the plant to plant distance, row to row distance. So plant to plant distance is given. Okay, in the problem, I think. Where is this? Here you can see 5.5. Okay, it is given. Okay, so 5.5 multiplied 5.5 and fraction 0.4. So you can see here water requirement is 49.28 liters per plants per day. Quite big amount because it is tree. Okay, it is tree. That's why you need more water. Okay, but if it is small, like vegetable, you may need 1 liter, 2 liter like this. Okay, I think clear now. Any question for this? Because you have a one question in the final, the similar type. Okay, this is very important. And marks is almost 20-30 marks. Okay. Any question for this step? Clear or not?
Clear, sir.
Okay. So once you have this one, you can see here very clear because this plant and this is the lateral, is it? Lateral is like this. Now you have a emitter here. You have a emitter here. So now you have to supply water. How much? In day 49.28 liter. You have to supply water. Second step is you have to choose the emitters. That's I call emitter selection. Okay, is very important. So when you choose the emitter selection, as I mentioned before this, I already explained, or is the all the formulas, everything. But one general calculation is like this. I have given here example. Okay, simply if you have to look the catalog, okay, emitters catalog like this one. Okay, you can see catalog. In the catalog, you can see here the minimum discharge is 0.5 liter, 0.55, and maximum is 0.8. So you can choose these emitters. Anyone you can choose, no problem. Then see what happen. Let's see if I choose one for easier. And then we have a 2, we have a 3, we have a 4, and we have a 8. You can see 1, 2, 3, 4, 8. I go for round 1. Okay. Now I need 49 liter, meaning that I have to supply 49 liter this plant here, this area. All right, this is my target. How I can find 49 liter? So this is the now combination of the combination of few things. Okay, combination of few things. One combination can be the time. Okay, just now I showed you the 1, 2, 4, 8. So this is a liter per hour. Liter per hour means if it is 2, so meaning the 2 liter per hour, and the time. So how long I can means how long I will irrigate. Let's say I will irrigate 4 hours. If I say 4 hours, time is 4 hours. And if I choose this 2, so meaning that every hour 4 multiply every hour is 2 liters. So 4 hours 4 multiply 2. So 8. We can supply 8 only. But we need how much? How much? 49. Then another option is what? In this plant, if we give the multiple emitters, let's say 6 emitters, 6 numbers. Now, if it is 6 emitters, 4 hours and 2 liter, then what will happen? So meaning that 2 multiply 4 hours multiply 6. So when the 6 multiply 4 is 24, 24 multiplied by 2 is 48. So 48 is close to 49. We will not get exactly like this, but we have to get the close one. Okay, something like this. All right, this is the one choice. So meaning that 3 things. Okay, one is the time, how many hours. Okay, time. Another is the number of emitters, number of emitters, number of emitters E. Okay, another one is the ditches. So these 3 combination. So another choice maybe if I choose Q equals to 4, time is 4, means 4 hours. What is mentioned means 4 multiplied 4 multiplied 4, it is 14. Then number of emitters is 3, so it is 48. Okay, so this one also can go, meaning that emitter we can change, not 2 liter, we can choose 4 liters. Okay, so that's why I have given here option. Let's say 2 applications. Okay, and oh sorry, another one is the application. Okay, application. Let's say I said 2 application. 2 application. If 2 application means morning and afternoon. Okay, so meaning that we have to multiply by again 2. If we multiply by 2, so it becomes 96. So meaning that we can reduce the emitters or reduce the time. Okay, maybe not 4. Here is 2 hour, 2 hours, 2 times. Okay, so this way we have to actually arrange it. Okay, clear the understanding concept? And to stop shortly. Is one clear or not? So there are I think 4 items. One is number of one is the queue, means what is the discharge. So you can choose 1 to 8. We have option 1 to 8 liter per hour. Okay. Second one is number of emitters. Number of emitters. Okay. I just write short form. Third one is operating time. Operating time or hour. Okay. Operating time. How many hours the system will run. Let's say you run the microirrigation system. How many hours? 2 hours, 3 hours, 4 hours. It depends on the person. Let's say you are available for 4 hours. So I can say 4 hours. Another say, no, I want to operate for 2 hours. So meaning that morning 2 hours, evening 2 hours. And you can say, no, I will run for only 4 hours. That's all. Okay. Then what is the queue? Number of operation. Another one is what? Operating time, queue, and the application. Okay. Number of application means how many times. Okay. Number of application is just 1 times, or maybe 2 times, or maybe 3 times in a day. So thus use this value. Let's say Q equals to number of emitters to, okay, operation time, let's say 4 hours. Number of application, let's say 2 times. Okay, then you multiply all of this. 2, 4, 2, 2, 2, 2, 4, 4, 4, 16. 16 multiplied to 32. Is it? But we need how much? 49. So this arrangement is not sufficient. All right. So then you have to change here. You have to change here. Maybe number of application you can increase, or maybe emitter number of emitters you can increase. Okay. Let's say number of emitters 3. 2 multiply 3, 6. 6 multiply 4, 24. 24 multiply 2, 48. 48. So it is close to this. Okay. So this 4 you have to adjust. And by adjusting, you can know, okay, whether this is the same or not. Then you have to say, okay, my emitter is this. What is the emitter? The discharge rate is 2. Number of emitters 3. Operating time is 4 hours. Application 2 times, morning and afternoon. So meaning that each plant you have 3 emitters. So if discharge required high, so you can use number of emitters in the same plant. Okay. So how to install? Install is very simple. Like this is the lateral. So you can install like this. Okay. Because this one you have to install manually. You cannot install like this. Okay. Otherwise, you can go different way. Let's say Q is high, 8. 8. Okay. You can see if I change it, if I change here. Okay. After this, I will stop. Okay. This, let's say Q is 8. I choose high discharge. Number of emitters 1. Operating time, let's say 4 hours or maybe 3 hours. 3 hours will be appropriate. And number of application 2. Then what will happen? 8 multiply 2, sorry, 3 is it? I said number of emitters 1, number operation time 3 hours. Okay, 3 hours. Number of application 2 times, means morning and afternoon. So then 8 multiply 1, 8. 8 multiply 3, 24. 24 multiply 2 is 48. So in this case, one emitter, one large emitter, but only one, 8. That's okay, fine. So this way you have to find the emitter selection. Then you can go here. Okay. Once you find, okay, let's say 8. Let's say this one. What is the 8? This is the 8. Once you find the 8, so okay, this is the maximum pressure. It should be 3 to 3.5. Okay, and you can see here constant. You can see K and X is given. Okay, and here also given the micro filter, those things. Another is a pressure. So this normally we need actually the two things is very important. One is need Q, another is pressure. So pressure is this one. Okay, and Q is 8, and pressure is 3.5. So let's say pressure is 3. So now you choose the emitters from the catalog, from the company, then see the pressure is like this. Then okay. Okay, so this is a second step. So second station, I will discuss you more about this. Now we have a step 3, 4, 5, 6, 7, 8. Okay, this step is very only step 3, 4 is important. After this is very easy. Okay, means easy to understand. So under step 1, 2, 3, 4 is very important. Okay, I think, do you have any questions? Then I can answer. Otherwise, we can start maybe 11, maybe 10:45 or 11 is up to you. Okay, try to come maybe 10:45. Okay, maybe we can start 10:50. All right. Any questions?
No questions, sir.
Okay, so we can start maybe 10:50. Yeah, not 45 for relax. Okay, so once it is finished, then you will have a detailed understanding about how to design the things. Okay, hopefully today you'll learn how to design the microirrigation system. All right. Okay, see you then 10:50. Yeah.
All right, sir.
All right. Okay. Okay, so can you see the slide now?
Yes, sir.
Okay, so we'll come back. Okay, so now we continue our micro irrigation development or design. Okay, you can say development, you can say design. Okay, all right. Okay, so I think before I discuss this thing, this is called crop coefficient. Okay, initial, then this is the mid or development and late. So when you do the development or design calculation, always our Kc value you have to take the maximum one. Okay, maximum. If you say initial, this is the value. Development means this is the value. Maximum is one. Okay, all right. So table is given. So you can find from the table. Then we need the soil. Okay, that we mentioned before. If you know the soil type, you can find the field capacity, available water here. Okay, or maybe this one. Field capacity, wilting point. Even you can find the available water. All right. Okay, so okay. Okay, I showed you this one. Okay, so you can see this specification that I discussed in the morning. This specification shows that this is the ditchers. Okay, this part is ditchers, and here is showing maximum working pressure. Okay, so meaning that you can choose these ditchers and this model. This is called model. You can see the deeper technical data. This is the model. 1, 2, 3. We have different models. Okay, but pressure should be maximum. This you cannot choose more than this. Or meaning that another way you have to understand that if you have a micro irrigation system, this is the field here, here is the emitters, and you have the pump. So you should have a pump. That pump will not create pressure more than this. So you have to choose the pump correctly. Yes, if you have a bigger pump, so maybe the big pump will give you more energy. When more energy, it will give more pressure. That is not correct. So you have to choose the right one. Okay, so maximum pressure should be this. So this is very important data also. So simply you cannot buy any pump. You should buy the right pump. Okay, there is another one I found. Where is this? Okay, let me check. Okay, this one. Okay, this is the maximum pressure. Okay, just now I showed you this one, maximum pressure. Okay, this one. So this one clear. Eh? This one mean if you have this data, is meaning that you have a micro irrigation system in the field and then you have a pump. So you should choose the right pump. The pump will not give more than this. If you give more than this, maybe your system will break down, or maybe discharge will not be uniform. Okay, maybe let's say the Q. What is the Q? Q, let's say 2 liter. Okay, 2 liter per hour. But when pressure is more than this, maybe here you can get 1, here you get 3, here you get 3.5. It's too highly variation. Okay, that can happen. Okay, it means that non-uniform. Okay, non-uniform. So that is not recommended. Okay, so this is the one. Okay, another type that I forgot to add in the slide. You can see this one. Okay, this one you can see. This one what says? This one doesn't say maximum. It says working pressure. Working pressure. So meaning that let's say you choose the emitter, this one, 2.3 means Q equals 2.3 3 liter per hour is this. So 0.5 to 4, meaning that your ACE emitter operating pressure is 0.5 to 4. 0.5 to 4 bar. You can see here bar. Okay, 4 bar. 0.4, 0.5 to 4 bar means it is 0.5 multiplied by 10. If you multiply by 10, so it is 5 to 40 bar. Okay, bar. What is the X value? You can see the X value is small, 0. Okay, previously I told you our slide that X value is 0.5 here. If down, what is the characteristics? It is called compensate, pressure compensate, meaning that if you change the pressure like 5 to 40, let's say this is the 5 and 40. Okay, here maybe 20. So meaning that your pressure is changing, but your discharge will not change. So it will be straight line like this. Okay, straight. Discharge is same. Pressure is changing, but discharge you will get 2.3. So meaning that if your pump work under different pressure, okay, your discharge will not be changing. So that is the meaning for this. Okay, so this is called compensate emitters. Okay, but previous one you can see the differences. It shows maximum pressure is 0.34, but it is X value is given. It is 0.46. It is not compensate actually. It is non-compensate pressure, meaning that this emitter, when you increase the pressure, the Q will change. But once the Q exceed 3.5, the Q will be unstable. Okay, like maybe it can go up like this. It will be very unstable. Okay, it will work only within this range. So this non-compensate. Okay, so that's how we have a different types of emitters. So you have to understand this. So from here you can know this is non-compensate, meaning that this emitters is very sensitive. You cannot operate pressure more than 4. So meaning that you have to choose your pump very carefully. Okay, you cannot choose very high capacity pump. Okay, you have to calculate. Okay. But next one it has a run. It has some range. It works like this. Within this should not be problem. Your discharge will be the same, something like this. So this is compensation. Okay, so this is the emitter selection. So when you choose the emitters, you see the catalog. From the catalog you can get this information. Okay, you can get the Q, you can get the pressure. Okay, so this is the range of emitters available. So meaning that if you choose, let's say 2.3, you have a different range like 0.5, 0.7, 0.8, 1, 2, 3. You have different types and this model. Okay, different models. Okay, and there are some other variation. You can see 0.4 to 5 bar. The wall thickness is like this. So you have a different thickness. Okay, so different models you will find. You have actually thousands of models, no problem. So from here you can choose the right emitters. So this is the one very important job. Okay, all right. Okay, now we go for our calculation. Okay, this is our calculation, I think here. Yeah. Okay, I think Okay, it is recording. Okay. Oh, recording is continuing. If I stop recording and start again, is it good? I think that is, or maybe continuing. Okay. Okay, let's continue. No problem. 2 hours 37 minutes. Okay. All right. Okay, so this is our slide. We come here, is it? Step 1, step 2. Any questions from here? Step 1, step 2. If not, then I move to second, third step. Okay. So this is the 1. Okay, but just now I showed you the two types of emitters. So one is the maximum. So if given like this, maximum working pressure like this, so meaning that this is non-compensate. Okay, this is called non-compensate. Okay, non-compensate emitters. And non-compensate. It's meaning that if pressure increases, discharge will vary. Okay. But another emitter types that will be given, it will say okay, this range. Okay, so meaning that pressure increase, but discharge will not increase. Okay, so from here you can choose any of these. Okay, but there is one understanding very important. Our soil type. If you see your soil type is sandy soil. Okay, sandy soil. Then try to choose the emitters low discharge this direction, not high. But if soil is clay soil, you can go down, means high discharge, because clay soil can hold more water. That's why if you supply water fast, means more discharge like 8 liter, 4 liter should not be problem because soil can hold it. But if sandy soil, if you supply more water, so water will go deeper. Okay, it will be lost. Okay, so you should not choose the 8 liter or maybe 4 liter for sandy soil. For sandy soil, if sandy soil, maybe you have to maximum is 3, 2. Okay, within this range. Okay, so this is one of the some understanding and skill, actually some experience. Okay, all right. Okay. Okay, and then third step. Okay, so second step is clear, meaning that we have to choose the emitter. Okay, emitter, and emitter we have to choose the four with the 4 options. One is what? Q. Second is the number of emitters. Okay, emitters. Third is the time, means operation, and 4 is application, means number of application. Okay, number of application. So these 4 things. So these 4 things, if you combine it, you can combine with this. Okay. This one is a previous one was 49. Actually, I opened the different slide now. Okay, because the reason was this value was not the same. Et is now little bit height. Okay, I think the same value. Yeah, same value. And now you can ask why it is 45. This 49, actually 55. What is 55? Because when I discussed before that when you design the micro irrigation system, the application uniformity, that is called one of the efficiency U, it is 90%. Okay, so this 49.28, 49.28, you have to divide by 0.9. When you divide by 0.9, you will get this 55. You can check it. Okay, this is called emission uniformity. Emission uniformity. Emission uniformity is 90% all the time. So when you develop or design micro irrigation system, it is 90% for micro irrigation system. So when you calculate, this is the actual calculation data, because in the field when you apply it, you cannot supply 2 liter everywhere. Okay, because let's say you choose the emitter 2 liter, you cannot supply 2 liter everywhere. There will be some variation, maybe 1.9, 2.1, 2.5, 1.9, 1.8. That's why there are some efficiency issue. So the efficiency is 0.9. Okay, so divide by 0.9, then you can find, actually I think 49.28 divided by 0.9. So it is 54.75. I have written here 55, round figure. Okay, clear now? This is the reason. Okay, so sorry. So this one is, yeah, divided by 0.9. Okay. Okay, so step 2. Then come to the step 3. Okay, so before I step 3 is was discharge through is lateral. So now you have chosen the emitters, is it? You have chosen the emitters. Okay, actually before step 2, there is another step. Actually, I miss it. Sometimes I put it this one at the beginning, step 1. Okay. Anyway, this is no problem. That one is called, maybe you can say step 3. Okay, this one may be step 4. Maybe step 4. This one may be 5. Okay, this one 6. Maybe this one 7. This one 8. Maybe this one is 9. Okay, step 4 is step 3. Okay, step 3. Step 3 is actually layout. Layout. What is the layout? You can see your questions. Your problem was what? Problem was 1 hectare land, 1 hectare land, and this is 5.5. So meaning that your land is 1 hectare, like this. So please clearly understand this one. So 1 hectare. It says each side is 100, meaning that this side is 100. This side also 100. But sometimes it can be this side is 500. Okay, this side is, let's say, 200. 200. If this side is 200, so maybe this side, sorry, this one is 50. It can be also, no problem. Okay, so we follow 100, 100. It's easy to understand. Okay, like this. 100, 100 means it is the same square size. Okay? So when you practice after this, you can change like this. But now I'm doing 100, 100. During your time, you can choose 50, 50, 200. Maybe here is not 50. Maybe here is 100. So meaning that 100 and 200. It is mean this. Then it is 2 hectare. Land is 2 hectare. No more 1 hectare. Because 2 multiply 1 is 2 and 4 is 20,000 meters square, means 2 hectare. So this one is 1 hectare. Okay, so you can change like this way. Okay, all right. So and the planting distance is this 5 and 5.5. Okay, so what is the layout then? Okay, so layout means, okay, I erase it here. So this is your field. Let's say I have a lateral, I have a lateral, I have a lateral, I have a lateral, I have a lateral. Okay, I just draw few. Okay, so normally you can say, okay, if it is not mentioned here, planted at spacing like this. So normally, if not given, so row to row, row is first, then column is later. Okay, so meaning that this is the row, this is the row, and then is this is the planting. Okay, planting means plant to plant distance, and this one is row to row distance. This row, and this one is a plant. Yeah, this one is a plant. So plant to plant distance, row to row distance. Okay, so if let's say this one is 100, this one is 100. Now you can see if 100, 100, let's say if I consider plant to plant distance is 5. Plant to plant distance is 5. If plant to plant distance is 5, so plant is planted along this and distance is 100. So what is the number of plants? Number of plants. Number of plants will be how many? It is length is 100 and you are planting every 5 meter, suppose. So it is 20. So meaning that every lateral, you have a 20 plants like this. Okay, 20 plants. Okay, so this is the things. And then it is a 5.5. 5.5 means this is the manifold. So if you divide by 5.5, how many? 100 by 5.5, 100 divided by 5.5. It is 18. 18, sorry. So meaning that you have a 18 laterals. 1, 2, 3, 4, 5 means 18 laterals. Okay, so this is very easy to understand. Okay, not difficult. Okay, okay, so sometimes it can be, let's say, different shape. Okay, different shape. Okay, so different shape. So maybe it is okay like this, like this. Okay, here is, let's say, 150. Here maybe 9. Here maybe, let's say, 90. So meaning that a lateral is 90. If lateral 90, so number of plants. Okay, I write short form plants. So lateral is 90. Plant to plant distance is plant to plant distance. Okay, plant to plant distance 5. So 90 divided by this 5. Okay, 5. So total is 18. So meaning that each lateral you have 18 plants. Okay, then how many laterals? Okay, so number of laterals, number of laterals, number of laterals is how many? This is the manifold because this is the width. So meaning that manifold like this. So it is 150. Okay, 150 divided by 5.5. Okay, so then you can find number of laterals. So this is actually layout. Okay, so you can choose the layout. Okay, so next step is actually layout. So layout you can specify. Okay, all right. Then after layout is you have to find ditches of lateral, because once you find the layout, you will find the lateral. Is it? Then your job is each lateral how much water you need. Each lateral. Once you finish the lateral, then you have to go for manifold. This is the manifold. Once manifold is finished, you have to go to the main line. One manifold is on main line is finished, you have to go to the pump. Okay, so this step by step. Okay, come to the next point. Okay, okay, so the solution I have given here. Okay, step 3 is layout. Okay, you can choose 1 hectare, you can choose 2 hectare. It should not be problem, but I choose here 2 hectares here. You can see 2 hectare. In the problem, I told you 1 hectare, but when I solve the problem, I choose it for 2 hectares. Okay. It doesn't matter. Okay, 1 hectare, 2 hectares. Okay, yeah. But normally, micro irrigation system is should not be more than one hectare or 2 hectares. Okay, 1 hectare is quite good. Maximum can be 2 hectare is okay, because if you have a bigger, then it will be problem. I will tell you later. Okay, let me finish first. Okay, so I think layout is clear. Okay, so layout means your field size. You have to know what is the width, what is the breadth. Okay, this one. After this, now you have to choose the, okay, once you finish the layout, then you have to choose, okay, lateral should be like this or should be like this. Understand my point? Because this is the layout. Now you can choose lateral this way. You can say, okay, I want to put lateral like this. Okay, or you can say, okay, I want to put lateral like this. Both way you can do. But one guideline that I told you last before, if your land is flat, you can go anyway. This way or this way, this way, no problem. But your land is sloping land. Okay, if land is slope like this, so manifold should be along the slope. This is the manifold. Okay, so see the slope of the land. Okay, another way is if this one is very long, like 200, 100. If 100, 100, no problem. But if 200, 100, now it is a questions now. Your manifold, let's say you want to put here or you want to put here or you have to put here. Okay, you have a number of options. Okay, if you put manifold left side, so meaning that your lateral is this one. Your lateral is 200. All right, clear now? Okay, please respond with me. And this case, if you like, if you those like, you can okay, you can camera on. Please okay, interact with me. Okay, when I ask some questions. Okay, so this thing you need to understand because so many options is here. So this one you have to be very clear. Okay, I'm telling that this is a layout because you are designing. You can say, okay, I want to give the lateral 100. Okay, if you go with the lateral 100, then what will happen? Then number of plants will be 100 divided by 5. So 20 plants. Okay, 20 plants means is row. This is lateral means actually row. Okay, when you say lateral, when you say lateral, so lateral means actually row means planted row. So meaning that this is the row. Okay, this is called row. This is called row. Okay, this is called plant to plant. Sorry, this is called row. So this is row to row distance. This is called row to row distance. Okay. Okay. So this is the plant to plant because row is going like this way. Okay. In this case, the row is like this. But it is a square shape, so no problem. Okay. All right. So in this case, see the example first. Okay. See the example, then you can change the option. Okay. So this is the layout. So we choose that. So layout once finish, then here I just assume that okay, lateral is 200, meaning that this is the lateral. Okay. If lateral is like this, 200, then you can say number of plants per lateral. And in the question is saying it is 5, is it? 5. So 20 divided by P to P. So 20. Okay. All right. So here is 5. Okay. This is the 0.9 is for emission uniformity. Okay. Emission uniformity. Okay. So one of the thing is that if you use 0.9 here, then this one no need. This one. This one no need. Okay. Then you have to choose this one. But if you use this figure, if you use 55, then here no need to multiply by 0.9. Okay. This is something. Okay. All right. So because of this 10%, okay, variation. Okay, that's why. So number of plants actually 200 divided by 5. Okay, so it is 36. Okay, I think here is a confusing, so better I recommend you not to consider here. Number of plants 200 because the lateral is 200. So it is that I will upload this file again after deleting this. Okay, in your MS Team. Okay, so it will be if we say 0.9 here, then 36. But if we say this one is 5, so it will be actually 40. Okay, 40 plan. Okay, so actually this is a 0.9. Actually, it is this one actually don't misunderstand sometimes. Okay, this one I consider actually, if you have a 200 meters, sometimes you can have a road, farm road or something. So there are some areas will not be considered. So you can say, okay, it is less. Okay, or you can use it. This is 1. Okay, if we say 1, it is 40. Okay, in this case 40. Okay, 40. So normal practice is this one no need. Okay. This one you can see here, it is not a uniform distribution. I forgot it. This is excess. Excess means when you plant it, you have some road. Okay, maybe for tractor machineries, you have some road. So when you have a road, we cannot grow it. Let's say we consider that 5% or 10% we have an excess road. So that is the meaning for this. Okay, you can consider. If you don't consider, no problem. Okay, so number of plants you can then determine lateral length divided by distance. Once you can detect this one. Okay, so in this case 0.9 is okay. Okay, 0.9, or maybe you can say what call 95 multiplied by 0.95 means 5% is road access. So meaning that here will be 38. All right. So once you know the number of plants, then you can find the volume of water required for this lateral. Why? Because this lateral, how many plants? 36 plants. Okay. This lateral have a 36 plants. And previously we found that each plant need 55 liters. Okay. This one 55 liters. Okay. If each plant is 55 liters, so discharge through the lateral. So this is meaning that we call QL. QL. QL equals, it is called LPD. LPD means liter per plant per day multiplied by number of plants. Number of plants. Okay. Number of plants. So LPD is 55. Number of plants is 36. Okay. So that is, we can find liter per plant per day. Okay. So means the liter per plant per day, or liter per hour, or you can calculate liter per second. No problem. Okay. Like this. Okay. You can see volume, flow rate per plant. This is flow rate per plant means this one is LPD that we calculated in the step 2. Okay. LPD, same as LPD, multiply by number of plants. Okay. So this one is, if you calculate it, it is 24 liter per plants. Okay. Why 24 multiply 36? Okay, why is it 24? Okay. Okay, so this one is, okay. You may confuse here. Why I push 24? Is it? Yes. Okay. Can you see here 49? Okay. So I just assume, let's say 49. It is, let's say 48. Okay. Because of 24, because we assume that we apply 48 two times. If we apply two times, meaning that 48 divided by 2, it is 24. Okay. Maybe one in the morning, another in the afternoon. That's why it is 24. Okay. So it comes from here actually. You can see 3 knots flow rate of emitters per application, 4 liter per hour, emitter discharge 4 liter per hour, 2 hours, 3 numbers, and 2 applications. Okay. Flow rate per applications. So okay, here is mentioned 2 applications. Okay, 2 applications. If 2 applications, so when you get 2 multiply 24. That's why our case is because total is 48. Okay, 49, we say 48. 48 divided by 2. Okay, that's why 24. All right. Then flow rate liter per minute per lateral. Okay. Okay, I remove this one. Okay. So I use this one, it's clear. Okay. So in this case, when you practice, maybe you can say your operation is one application. If it is one application, so here is not 24. Here you have to say 48. All right, 48 per liter per plant. But when it's a two applications in the morning and afternoon, so meaning that I have to find 24 morning, 24 in the uh, afternoon. So meaning that two applications. So meaning that 24 plus 24, 48. So 48 we have to supply every day. Okay, that's why it is 24. Okay, each plant is 24. How many plants? 36. So multiply by 36. So this is the 864 liters for each lateral. Each lateral. Okay, so meaning that this lateral, the QL is this amount. Okay, 468 liter. Okay, per day. So this per day now you have to calculate the per minute or maybe per second. Okay, because we operate for how many hours? 4 hours total. Okay, maybe 2 hours, 2 hours. Okay, so that's why here 864 total liter. 864 divided by 2 hours multiply by 60 means minute. So we can get 7.2 liter per minute. Okay, and here 7.2 divided by EU. EU means emission uniformity. Okay, emission uniformity. Emission uniformity is 90%. Okay, because in the previous calculation is 48. If we divide by zero point 0.9, it is 55. But here we consider actually 48. So we have to divide by emission uniformity here. But if we consider 55 here, 55, this one, instead of 24, then we don't need to divide by here. Okay, so this is the things. This remember it. Okay. So actually, what is our purpose for the lateral? Okay, so actually we have to design the lateral. Okay, and design the lateral means okay, there are few things you have to okay, find. One is I feel cold actually. My AC switched. Okay, just a minute. AC drop on my head. Okay. When you say lateral, you can say lateral design. Okay, when you say lateral design, there are few things. Every items has the specification. What is the specification? First is what is the Q? Q means lateral discharge. That is called liter per minute. Okay, so QL is 8 liter per minute. 8 liter per minute. Okay, so meaning that we have a lateral. We have a lateral. So this is lateral. This is the manifold, is it? This is the manifold. So when you connect the lateral with manifold, so each lateral will get 8 liter per minute. Each lateral. Okay. Once you have the Q, then you have to choose the diameter. What is the diameter of the lateral? You have to find it. Okay. Then you have to find the energy loss. ACFL. Energy loss. So QL, D and ACFL. ACFL is called head loss. Okay. Head loss or energy loss. What is head loss actually? Head loss means like if we run one place to other place, we lose the energy that I mentioned before during the hydraulics. So similarly, when water moves from one place to other place through the pipe, okay, it loses the energy. Last time I told you like this, energy losses like this, L by D, V square by 2G. Okay, this formula I mentioned before last time that you can, this is the ACFL, you can find it. Okay, you can see the L is 200. D is the diameter, we have to find it. Once you know the diameter, V is the velocity of water, then we can find the ACF. Okay, so these three things you have to find. from the, because if we find these three things, then because we have to buy the pipe, is it, for this? Okay, what are the diameter of the pipe we have to buy? Okay, so it depends on the ditches. Okay, so that's why these three things we have to find now: Q, D, and H. Okay, now see how to find this thing. Okay, I think Q is clear, is it? How to find Q? Clear now? You find the LPD. Okay, once you find the LPD, then it is very easy. See the length of the lateral divided by row to plant distance. Then you can, and this 0.9 is optional. If you can choose excess road excess, let's say 0.9 or maybe just 5%, so it will be 0.95. Okay, then you can choose like this. But if you say my lateral is like this, then this one should be 100 divided by this. Okay, no problem. So this is the way you can find number of plants. Okay, so your lateral should be this way or lateral should be this way. Okay, there is another way you can find. Okay, number of plants you can see. Okay, number of plants. Okay, you can find this one actually we call total plants. Okay, you can see here total area. Total area is 10,000 meters square. 10,000 meters square. And row to row and plant to plant is 5 multiply 5.5. So you can find the total plants. Okay, like here you can find also. You can see number of plants per lateral is 36. Okay, so now you can see you can divide by 10,000. 10,000 divided by 5 divided by 5.5. Okay, multiply by 0.9. 0.9 means excess, so it is 327. 3 to total 3.27 plants. Okay, now you can see if you know this is the lateral, so how many laterals then we have? Laterals we have then this is the 100 because this is the manifold, so lateral is every 5.5, is it? So 100 divided by 5 by 5. 100 divided by 5.5. So we have 18 laterals. 18 laterals multiply by each lateral is 36. Each lateral is 36. So 18 multiplied by 36. 18 multiply 36. Okay. This is a what is called 36 number of plants 36. Okay. Did I do mistake? 6.63 to why this thing happened? 18. You can see the number of laterals then. Number of laterals means this is the manifold. So every 5 meters, so it is so every 5.5 meter, is it? So it is 18. Okay, 18. All right, so then okay, I come this one later. I think I did a mistake in the calculation. 5. Okay. Oh, here is not one. Here is two actually. 20,000 hectare. You can see here this is 327, and here is 18 is 6. Not 327. It will be 654. 654. Sorry, 654. So here is 648. Okay, almost close. Okay, so this is also you can find the total number of plants. Okay, you can find. All right. So meaning the total area divided by plant area, because one plant area is what, row by row multiplied by plant. Okay, that was you know this. Okay, so next is okay, next is you can see here. So we from the appendix. Okay, we have to find. Okay, so our Q is clear now. Q we can find. Q is clear or not? Everyone, do you have any questions for the Q? How to find the lateral ditches?
No question, sir.
No, sir.
So clear?
Yes, sir.
Okay. So Q will actually mainly LPD that we found the crop water requirement multiplied by number of plants. Okay. Number of plants is row. Okay. So this is the QL. Okay. Next step is, as I mentioned, three things we have to determine. One is the Q, another is the diameter, another is the A shape. Okay. Okay. Let's see diameter. Okay. When you choose the diameter, so diameter you can determine different ways. Okay, one way is you can see here what is called okay, Q. Okay, I show the what is the actual way. Okay, here you can see this table. Can you see this table? Okay, so I have given the book actually in your uh, okay, in the MS Teams. Also I have given one chapter, so this chapter it is available, this table. Okay, this table actually, okay, what is the characteristics of this table? You can see here. You can see this row, this one is a Q. Okay, this is a Q. This one also Q, but this one is Q in liter per minute. This one Q in liter per second. Okay, so this two is Q. So meaning that in the calculation we found what is the value? 8 point here, 7.2, is it? 7.2. You can see here liter per minute. Liter per minute. So what is the 7? 7 is, you see the 8, 6 and 8. So you can put 8. Okay, because closest higher. Let's say you're 7 point something, you can put 8, no problem. Okay, so 8 or 7.2. Okay, the value comes from there. Once you choose the 7, means 8. Then next you can see here this one. You can see here ID, 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 ID. ID means internal diameter. Means pipe. We have a pipe. We have internal diameter, external diameter. This is internal diameter. So internal diameter is 15.8, 20.9, 26.6, 30.1, 40.9. So you have a 5 diameters here. Okay. Then if not available, you can go then again. This diameter is higher. 108, 108, 160, 219, 208, 273, 259. So you have a series of different diameters. Okay. So this is the diameters. So then you can choose the diameter based on your Q. First, you mark your Q. Where is your Q? You mark your Q first. Then you draw the line like this that I have done here. Okay. Now you can choose the Q. Any Q you can choose. Let's say this one. Let's say this one. Okay. You can choose anyone. Try to understand what is this. Okay. Then it will be clear for you. Okay. Let's say if I choose ID internal diameter means pipe diameter 15.8. 15.8. So meaning that pipe diameter is 15.8. This is a millimeter. Okay, this is a millimeter. You can see here, written millimeter, diameter millimeter here. Okay, so this one is millimeter. Okay, you can see the east diameter. You have a two columns. One is this B, another is Z. Two B and Z. Okay, I write here. One is B, another is Z. Is you can see here also B, Z, B, Z. Okay. Okay. All right. So what is your job then? You find the Q. Okay. You find the Q 7.2 that we find. You mark your discharge and draw the line like this. Select the row. Let's say 7.2. I choose 8. So I choose this line. Second, I will take the diameter, any diameter. I can take this, I can take this, I can take this. But when I choose the diameter, make sure, let's say I choose the diameter this one. So I will come until here. This is my value, true value. True value, what is this? One is V, another is Z. So what is the V from here? Can you read from your computer? You can see here V 0.68, is it?
Yes.
Okay, so V is 0.68. I just write here. So V is means velocity. It is called meter per second. Okay. All right. Then Z, you can see the Z. What is the Z value here? 3.94, is it? Clear? 3.94 here. What is 3.94? J is what? J you can see here, meter per 100 meter. Meter per 100 meter. What is meter per 100 meter? It meaning that, let's say your pipe is lateral is how long? 200 meter, is it? Your lateral is 200 meter. Am I right? This one? 200, is it? Okay. If lateral is 200. Okay, where is this? We came here, is it? This place. Okay, so lateral is 200. Okay, so let's say this is 100. This is here 200. So this meaning that every 100 meter, 3.94, meaning that when water comes from this point, let's say this is 0. When water comes from 0 to 100 meter, its loss is 3.94. 3.94. It meaning that, let's say when your pump is running, then water coming from this is the manifold. This is the manifold. So water going to is lateral, is it? This is the lateral. Okay, this lateral, this lateral, this one also lateral. So when it is enters, let's say here there is energy. Let's say energy is 70. Energy is 70. So every 100 meters, 3.94 lost. So meaning that, like if we run, we lose the energy. So when water moves from one place to other place, water also lose the energy. So 70 minus every 100 meter is 3.94 loss. So 3.94 here, 3.94 here, every 100 meter. So finally, here will be 70 minus 3.98 multiplied by 2. Here will be 62. 62.04. Meaning that when system will run the water, at the beginning of lateral. So when this water reaches to end of the lateral, the energy will lose. It will be 72. It will come 62.04 because the energy loss is 394 by 100 every 100 meter. Okay, and velocity is this. Okay, if you see the next one means it is 15.8. Diameter is so meaning that this one diameter is 15.8 millimeter. So meaning that if we choose this diameter, if we choose this pipe Q, so diameter is this, the head loss is this Z. Actually Z is a head loss. Okay, Z means A shape. Okay, so we can calculate then A shape L. Okay, A shape L means this Z multiply by length of the lateral. Okay, Z is 3.94 by 100, is it? 3.94 by 100, and L equals lateral length. Length of the lateral is 200, is it? 0 to 200. So 200. So it is 6 point, what is this? 3.94 multiplied by 2. 3.94 multiplied by 2. It is 7.88. Okay. 7.88. Okay. So this is the loss. This is the loss. Okay. This is the loss. So this 7.8 means total loss. Total loss along the lateral. But J, when you say J is loss every 100 meter. Okay. So this table gives you J, that is every 100 meters. Sometimes your lateral can be 500. So just you multiply by 5, then it is easy to calculate. Okay. So meaning that what is the value we find from here? J value multiply by what is called lateral length. Okay, Z divided by lateral length, actually A shape L. Okay, so then A shape L we can calculate. So clear this one. I'll give you another example. This one clear or confusing?
Another example lah, sir.
Okay, let's see the second example. When okay, this one okay, D is 15.8. Now let's say D equals 20.9, meaning that D is increasing. Okay, D is increasing. When D increase, what happens? Similar way. Okay, let's say D equals what? 20.9. 20.9. Okay, so third one I will ask you, you will give the answer. I explain the second one. Okay, D is 20.9. If D is 20.9, so what is the V value then? My Q is same. My Q is still 8 because Q will not change. But I have option, I can choose different diameter. Okay, if D is 29, so what is the V value from the table? Could you please read?
0.39.
Okay, very good. 3.9. So this is meter per second. What is the Z value?
1.
1. Okay, very good. You can see some difference here. Meter per 100 meter. Okay, you can see here when diameter 15.8, V is 0.68 and V is here 0.39. It's less, is it? You can see Z 3.94. Here is 75% less almost, because 3.94 means 4 actually. Here is 1/4. Can you imagine how the difference? Okay. Then if you see if you increase the diameter again, you can see 26.6. You can see the V is 0.24. Okay. Here is 1.39. Then again, velocity decreasing, and J is 0.31. J is 0.31. So meaning that when diameter increasing, the energy loss will decrease. Okay. All right. So that's why sometimes you have to compromise which one you have to choose. Okay. Not so high, not so low. Because the first one energy loss is too high. This one, 3.9. Okay. 3.9. You will see what is the problem. Just remember this value, 3.9. The value is 3.9. So each lateral is 200 meters. So total energy loss is 7.8. Okay, one lateral is 7.8. Second diameter is 1. So total is then 1 for 100 meters. So it is 2 meter for total, is it? Total HFL. Because if I multiply J here, J is 1, because 1 by 1 means 1 by 100, and L is 200. So 2 to cut. So it is 2 multiply 1 is 2. Okay, 2. Okay, so I think got some understanding. Okay, now I want to explain another thing. You can see there are some area is shaded area. Can you see here? This one, this one, this one. Okay, here also. Can you find any difference, the shaded area and other area? Can you see any differences? You can see the written, you can see the writing here. Last, this line. The velocities above or over 1.5 meter per second are not recommended. That is called shaded area. So shaded area, you can see all the shaded area, the velocity is more than 1.5. You can see here 1.53, 1.7, 1.51, 1.82, 2.3. Okay, all are shaded area. Clear now?
Yes, sir.
Okay, let's say, let's say your Q is, I just finish here. Let's say your Q is 26 liter per minute. This one. All right. Now it falls within the shaded area, this one. So meaning that this diameter is not recommended. This is not recommended. So you have to come, your first diameter should be 20. This one, or this one out of this three. But first one is not recommended because the velocity is more than 1.5. Okay, so there are there are few informations from here. Okay, hopefully clear. Okay, now I remove it, and now I can show you why this thing. Okay, I think clear this one. I removed something here. Okay, now I think I'm not sure whether still you can remember or not. Okay. When I explain the hydraulics, I wrote this formula, something like this. LD V square by YZ. You see what is the meaning this? You can see here when D increasing, you can see internal diameter when D increasing, the A shape. A shape means actually what? A shape means it is a Z also, is it? A shape meaning A shape actually J multiply by length of the lateral. Okay, means length of the pipe. Okay, you can simply say it is length. Okay, length of the lateral. So when you calculate for lateral, it is length of the lateral. When you calculate for manifold, it is length of the manifold. When you calculate for the main pipe, it is length of the main pipe. It is the same way. Means all pipe when you design, it is the same way. Okay, so meaning that this A shape actually the J. Okay, so meaning that it is J. It is actually J. Okay, J is every 100 meters. So you can see here when diameter increasing, J is what? J is decreasing, is it? You can see here diameter is 15.3. J was 3.94. When diameter is 20 means diameter increasing, J is 1 decreasing. So meaning that you can see diameter. So meaning that J decreasing means H decrease. Okay, because J is proportional to H F. That's why you can see here D. When D is increasing, because D is the denominator, so HF will decrease. Okay, when D is increasing. Okay, this is the one point. Second point is also you can see when when diameter is increasing, velocity also decreasing. Sorry, yeah, velocity is decreasing. You can see here 0.68, 0.39, 0.24, 0.14, 0.1. So this is a good. Why? Because when decrease, velocity decrease, this one is decrease. Sorry, when velocity decrease, this one is also decrease. Okay, so meaning that velocity decrease, A shape also decrease, because when you design, we have to think always our A shape should be minimized. It should be minimized, not increasing. Okay, this is very important, because if you have a more loss, so meaning that you have to pay more. Okay, more loss. Okay, loss is not good. So A shape actually loss, energy loss. So meaning that when you transfer water from one place to another, it loses too much energy. If loses too much energy, meaning that we have to buy the big pump. So when you buy big pump, then you have to pay more for energy cost, pumping cost, everything. Okay. So our purpose is minimize this A shape. Okay. So this is the some information when we choose the A shape. Okay. Okay. So first thing, just to normal way, what I can say, if you see the Z value is more than 1, then you change the diameter, means next one. So it is 1 or less is good. Okay. So in this case, 15.8 is not comfortable. I think 20.9 or 26.6, this is a more better, because this one Z value is 1 and here is 0.31. It's quite good. But this one is 3.9, is too high. Okay, so just get some understanding. Okay, because of this formula. So this table actually developed based on this formula. Okay, this one. And the velocity is when velocity is more than 1.5, the loss is too high, because it is a square. Okay, if v is 1, if you put v square, it is 1. But if v is 1.5 and more, so v square is what? 1.5 square. Okay, so this one will increase more and more. Okay, so that's a velocity more than 1.5 is not recommended. Okay, because it makes a system unstable and it can start shaking. Sometimes you can see water flowing. When water flows, you can see some sound. Okay, sometimes, not always. So that is the symptom for this when velocity is high. Okay, that thing happen. Okay, so this is the way we have to find actually. Okay, ace. Okay, so this is that's I have given here 3 tiles. Okay, the first one, second one, third one. So let's just choose this one. Okay, you can see Z is 0.31, Z is 0.08, 0.04. I didn't choose very small one. Because if we very small, then B will be very small. If B is very small, there is another problem also. If B is very small, then you can see, the in the water there are some sediments, very small particles. Okay. If B is very small, then small particles, then this one will sedimented on the surface. Then the pipe will be slowly blocked. Okay. That's a too small is not good. Okay. So choose this one. All right. So D is this finally. And then we can find the total loss because I told you we have to find 3 things. First is Q, diameter, then A shape. And then A shape is length of lateral multiplied by Z. Okay. There is another factor actually, F. So you have to use this one when you calculate the total A cell. What is the F actually? If you want to find the AF, you have to come this table. Okay, this one. This equation. Either you can use this equation or this table. Okay. When you use this equation, then you can see here M and N. There are 2 things. M and N. N means your lateral. Your lateral. How many meters? 36 or 40 meters, is it? Or maybe 50. So this is number of emitters. N means number of emitters. Okay. N is number of emitters. And M, what is the M? M is actually this factor. You can see here 1.8 and M is 2. So your case M is 2. Okay. Why 2? Because Darcy-Weisbach equation means this equation. That equation I just wrote it. Okay. This equation. This equation actually Darcy's Weisbach equation. So the M is 2. That's why it is 2. So you can use this formula. You can calculate it. Let's say your lateral, this is a lateral, you have a 40 meters. N is 40. Let's say you have a 70 meters. So N is 70. You can calculate. Otherwise, you can come here. Let's say you have a 40 meters. So this 40. This Darcy. The value is this one. 0.35. If more than 100, value is 0.3. Is the constant. Okay. 0.33. Okay. So this value you have to multiply. Okay. This value. Then you can get the head loss. Okay, because the head loss is very small. Okay. Okay. If you go for velocity is high, let's say this one is D is 108. Okay, 108 means we choose this one here 108. But if we choose D equals maybe previous one, okay, 108. This is the first one. Maybe if we choose let's say 40, Then here is 3, but 3 is not here. Let's say if I choose this 2.9, 2.92, this one is not valid because shadow. Okay, maybe in between there are some other pipe is available. 1.108, 40, maybe 60, 80, 100. Okay, in between. If we go in between, then the value, this Z value will be higher. Okay, there is another table is available. Okay, so this way you can find the this value. So this is the total losses. You can see now multiply by this 18 means number of laterals, because this calculation for one lateral, and then because we have a 18 laterals, because this is the 100 divided by 5.5, is it? So it is 18, because each lateral is 200 meter. So if we have 18, so 200 multiplied by 18. So this is the length of the total lateral. So that's how we multiply by length of the laterals, 18 multiply by, okay. Actually here is not 100, actually there is some small mistake here. Actually it should be 2, because our lateral is 200 here. Because I mix up, because in the question I says 1 hectare, but when I did here 2 hectare. Okay, so that's it. So it should be 200 meter. Okay, so then the here will be double 1.84, I think will be double. Okay, so it should be 2 multiply 0.31 multiply 0.33 multiply 18. So it will be 3.68 for 200. But if 100, then it is 1.84. Okay. Okay, clear the letter or not?
Clear.
Okay, if clear, then very good. Next step. Next step is manifold. So where is our manifold? 200 or 100? Because previous one lateral was 200, is it? So manifold is this one, is it? Am I right? So manifold is 100. That's why manifold is 100. So manifold is same like lateral. So manifold, we have to find the manifold length. Manifold, I say QM. Previously I said QL. QL means discharge for lateral. QM means discharge for manifold. Then DM means diameter of the manifold. Then HM. HFM. Here is QL. Then DL. Then HFL. Okay, similar way. So the step is same here. Now you can see manifold length is 100 meter. Okay, because this is the lateral. This is the lateral. So manifold connect the lateral. So manifold is 100 from here to here. Okay, clear. Now, okay, number of laterals, we can find it same way. Okay, because we have already laterals we have find, so this one is not necessary in this line. Now you have to find the volume of how much water is coming here. How much water? Each lateral is what? Previously, each lateral is 7.2. Okay, very simple. Each lateral is 7.2. How many laterals we have? 18. If 18 laterals and each lateral is 7.2, just multiply it. Then we can get this QM. Okay, 7.2 multiplied by 18. So it is 1296. Oh, sorry. 12 QM. What is the QM? Okay, 7.2, or you mentioned here 8 or 20. It is 160. It's fine, no problem. Okay, but if you calculate exactly 7.2, just multiply by 18. Okay, this okay, no problem. Okay, this just for some safety factor, I just added something. Okay, so this is a QM complete. Once QM come, so same way you have to find the DM. Means same table. How we choose QM, then you can come the return. So this is the Q. Then you choose the diameter and choose the V and choose the Z value. Okay. Once you choose the Z value, then you can find the A shape. A shape equals Z multiplied by length of manifold. So manifold is only 100 meters. So multiple. So you can find the things and then multiply by F. This F again. F. Then you can find this. So you can find all of this. Okay, manifold. Clear this manifold? Okay, thank you. So next step is main line. Okay, so this is the layout. Okay, so this is our lateral. These are lateral. These are lateral, and we have a emitters. We have a manifold now. Now main line. Let's say main line is 500 meter here. Let's say here is the pump, and from pump here is okay 500 meter. So this is the same way. Okay, because only one line. So the main line and manifold discharge is same, meaning that Q. Okay, when main line I write Q equals Q, capital Q. Previously I wrote QL lateral, QM manifold. I write now Q. This means main, or sometimes we call system. Okay, system. So Q is actually QM. In this case, you can see here because same pipe is connecting here. Okay, but diameter it can be the same because only one, so the same diameter. Okay, but one thing is difference here. When you calculate the loss, okay, A is M. I just write capital M. Okay, means main, and this is manifold small m. Here is Z multiplied by L. Okay, so this Z maybe you can use the same diameter of manifold. Fine, or maybe you can use one size bigger than manifold. Also is okay. Same diameter also okay because only one line. All right, but here F. What is the F? Okay, you can see the manifold. This one. When you see the layout, okay, this is the main line. Okay, let's say here is a manifold. So manifold we have a some lateral, is it? You can see N. N means number of emitters, but when you say manifold, it is number of laterals. Actually, N means number of openings. Okay, opening means you can see a number of outlets. Opening means outlets. So meaning that I have a lateral, so I have a manifolds, I have an outlet. like this. I have 18 outlets because 18 laterals. Okay, I have a laterals, but each lateral I have a, let's say, 36 emitters. So meaning that I have 36 outlets. Here 36 outlets. Okay, outlets. Okay, here I have a 18 outlets because 18 laterals. So I have 18 outlets. 18 outlets. So when you calculate the lateral ACFL, so 18 means 20. So your value is somewhere here, 367 or here. But you can see main line. Main line is how many outlet? Only one, is it? In and out, is it? So value is 1. You can see here 1. So F is 1. Okay. So this is the difference. That's why in the formula, normally when you calculate the formula, when we calculate the main pipe, it is F, so we don't consider it. Okay. Consider means because value is 1. If we put 1, it is same. But in the book, doesn't mention it. Okay, so the reason is 1 outlet, so value is 1. Okay, so this is the thing. Okay, so in this case, if for main, so main pipe, so normally it is written like this: J multiplied by L, meaning the same thing. Doesn't say about F. Actually, F means 1. Okay, so this is the thing. All right, so then you can calculate the main line. Complete. So main line also similar way. You have to find the Q. Q means QS. You have to find the D. You have to find the S. So similar way. Next step is you have to calculate the total dynamic head. Okay, I think I gave little discussion about the total dynamic head when the pumping selection is it, how to select the total dynamic head. Okay, and I have given also pump lecture in the PowerPoint, that link. Maybe you can listen again. So total dynamic head. So this total dynamic head, actually the head required energy for everything. Okay, means what is the energy at the from the beginning to the end, means from pump to the emitter. Okay, so all of the losses you have to consider. Okay, so what is the total dynamic head? You can see here, next slide. Total dynamic head is this. Okay, this one I discuss later. You can see A shape. A shape is what? Major loss and minor losses. Sorry, this one is not O, it is I. Minor losses. Major loss and minor loss. Okay. So all of this that I calculated, ACFL, ACFM, okay, then ACF means main. This is called main pipe. This one is main. This one is manifold. This one is lateral. So all together is ACE. Maybe you can say capital ACFL. Okay. Another one is called minor losses. That one is ACE FM, small n. Capital A, small m. Minor losses means, I told you the fittings, elbow, okay, those losses. Because when you have a pipeline, you have a 200 meter pipeline, lateral is it? And this pipeline 200 meter is not the one pipe. You have a joint, okay? Every 6 meter you have a joint. like this. Or maybe you have some gate line, gate valve, you have some pressure, you have a filter, you have injectors. Okay, so this meaning that actually uh, all the fittings available, so all the minor losses you have to count it. So roughly you have to calculate it. Okay, let's say one fittings minor loss is 0.1. Let's say 0.1. Let's say you have a 500 fittings, so multiply by 500. Okay, then you can get it, this one. Okay, and this one is elevation AC HB. HB is the velocity. So when you choose the velocity, okay, water flowing in the pipeline. So velocity is means v square by 2 g. Okay, okay, this is the HV. Because each pipe, when you when you select the pipe, each pipe you get the V, is it? So based on the V, you can calculate the HV like this. Okay, so maybe you have a main line, you have a manifold, you have a lateral. You can calculate. You can calculate differently. Then you can make average. Okay, but most of the cases we take the HV is for lateral. Okay, the V is for lateral. So HV. Okay, okay. So this is the HV. Okay. And this one is, I forgot AC. What is this? Is this mentioned? Okay, just a minute. AC is, okay. So this middle losses. Okay, this one is the pump. Okay. Let's say your pump is, let's say this is the water source, is your pump, and this is the surface. Okay, and let's say this is the pump. So the ACS is a pump to water surface distance. Okay, this distance is called ACS. Okay, AC is pump to your land. Let's say your land is here. Your land is here. So this pump center of the pump to the elevation of the land. So this one is AC. Okay, and this one I think this is the slope actually. Okay, elevation means land, because your land can be sloping, not the flat. Your land can be like slope. So this elevation, but this one can be plus minus. If downward, it can be minus. If upward, it can be plus. Okay, so this all of this actually total dynamic head. Okay, okay, clear now or not clear? Please ask me. I will explain that point. Total dynamic head. This total dynamic head I didn't mention before. Mention here clear means details, because I have given the pump. Okay, pump lecture. Please look the lecture pump. Okay, pump selection. So where you can find details how to find the total dynamic head. Okay, so meaning that every system when you calculate, you have to calculate the total dynamic head. So got some understanding? I will explain after this more. Okay, means briefly, have you understood or not? ACS means, let's say you have a water source. Let's say your water source is here. Okay, let's say you have a pump here. Okay, this is the pump. So means pump center to the water surface. Okay, this is S. Okay, this is the ACS. This is the vertical distance. But sometimes your pump can be far away, not at the here. Maybe pump is, let's say, from the water source. After this, it is a horizontal pump is here. The distance is, let's say, something like 2 kilometers. When it is 2 kilometers, So then you have to calculate the A shape, because it will be considered as a pipe. Okay, this formula you have to come. Okay, this is gamma L D. L is the length of the pipe, D is the diameter of the pipe, B is the velocity. So velocity, this velocity and main pipeline velocity is the same. Okay, so you can calculate this one. But this one actually, when you buy the pipe, so manufacturers will give you this one. Okay, then you can find it. Okay, A shape. All right. Okay, then AC is, it is the elevation of the land. Let's say your pump is here, then your land is, let's say 2 meter high or 5 meter high, or maybe you are sending the water to the hill. Okay, so let's say your land is here. So meaning that from here to here, this elevation. Okay, so then if it is like this, maybe your pipeline goes like this. Okay, this is the pipe length, but this height is the vertical height. Okay, and this A shape, I just calculated all the lateral, manifold, mainline, all. And HB is the velocity. So then you can get the total dynamic head. Once you get the total dynamic head, the step 8 is this formula. This formula you can find the water horsepower. Okay, I think I explained it before. Okay, this one. This Q means what? This Q means your system Q, means actually QM. Okay, Q manifold. Q manifold is same as Q system. Okay, in this case, because this is because only one manifold, that's why it is same. So meaning that this one. Okay, so this Q is this one, TDS is this one, then you can find this one. So this is means this is the kilowatt. You can see the current with electricity. So meaning that to run this system, we need this amount of this kilowatt, means number. This from this calculation, it is, let's say, some this this is the kilowatt. Okay, so this kilowatt is required. Okay, so this kilowatt then will produce the energy. Then we have to use this one. Okay, brake horsepower means pump out. Actually, this one is this one. WP divided by N. N is normally it is 70%, 0.7. Okay. So N is equals 0.7. 1.7, then you can find this. Okay. So this is the last one, pump design. Once pump design, then finally is the layout. So you have to draw this layout like pump, filter, then manifold, this lateral. Then you have to show this is the emitter, this is the plant to plant distance, lateral to lateral distance. So this one you must draw it. This is the 100, this is the 100 or maybe 200. So you should give this layout. Then those will install, they will understand, okay, what to do. Okay, and same is you have to provide the some specification. What is the diameter of this manifold? What is the diameter of the lateral? Okay, yeah, this thing you have to provide. Okay, here is actually given all of this. They say what is this? Fiction losses, fiction losses. The same thing. Okay, but this Q and P has a different formula, like this, like this, like this. But you can see the unit is not same. Here is liter per second. Here is meter cube per second. Okay, so that's why Hectare is different. Okay, here is feet. So here is different. Okay, so I prefer this one is easier. Okay, so we can have a different what called layout. Okay. Okay, now the question is, okay, this is a different type of emitters. You can watch it here. Okay, I have given some link. Okay. Okay, so one thing that I want to mention, let's say if we have a two plot, because we just finished the calculation for 2 hectare or 1 hectare. Let's say we have a two, this one 2 hectare and 2 hectare. So meaning that two different field. Two different field means we have a two manifold. This is the one manifold, this is the another manifold. Clear now? Okay, so meaning that this is a 2 hectare, this is a 2 hectare. Okay, so meaning that now we can say the same example. If you have a 4 hectare land, so what you will do? So first thing in my recommendation is if you have a 4 hectare land, let's say this is the 4 hectare, you split it to make it 2 hectare, 2 hectare. Okay, otherwise you can make four. Everyone is 1 hectare, 1 hectare, 1 hectare, 1 hectare. Okay, it depends what you will do. If you want to say you want to grow the two crops, okay, I recommend to better to do two. Okay, okay, let's say two crops. This is one crop A, crop B. But you can say you can do also 4 hectare. You can make four because 2 hectare, 2 hectare is it? I can say 1 hectare, 1 hectare, 1 hectare, 1 hectare. It is some planning. I just this thing I will explain now because time is going to finish. Okay, just few minutes. You can get some understanding. Okay, you see the reason. Okay, because we design for one manifold, is it? One manifold. Let's say we come here 4 hectares. So now we have a two manifold, and this is my pump. Okay, so now my main line is coming here. Okay, so I can go this, I can go this. Okay, so now you can see the ditches previous. What is that? What was the ditches? You mainline ditches. What is the ditches? Mainline 2.6 means because of one manifold, so it is 2.6. 2.6 is coming manifold. Okay, 2.67 liter per second. Remember. Okay, now I come to here. This is 2. So meaning that if this one is 2.67, this field 2.67, meaning that 2.67 here, this one. Okay, this 2.67 means this manifold, and this manifold also 2.67. So meaning that 2. So meaning that 2.67 multiplied by 2.6. Sorry, 2.67 multiplied by 2. What is the value? 2.67 multiplied by 2. So it is 5.34. So meaning that main line is not same now. 3.4 because we have a 2. But it is a depends on you whether you want to supply water both same time. If you supply both same time, then you design for 5.34. But if you plan, I have a 4 hectare, I will supply water one by one. I'll supply 2 hectare, then I stop here. Then once finish, this one stop, this one. Then in this case, the main line will be the same as previous one. No need to increase the pipeline because you don't need 5.34. You need 2.67. You need 5.34 supply when you irrigate both, means all 4 hectares same time. If like this, so meaning that your pump size will be bigger because your discharge is 5.34, here is 2.64. So when you want to supply more water, you need a bigger pump. So meaning that you have to buy big pump, more money. Understand? So this is your uh, concept. Something is experience, skills, or your what is called understanding, or maybe you can say your art of design, art. Okay, this is very important. So this art is person to person is will vary. Okay, this is the thing. This is the one option. Second option, I can say you can say 4, 1 hectare, 1 hectare, 1 hectare, 1 hectare. And the person says, no, my pump is very big. I cannot afford it. The pump is expensive. Maybe it's 10,000. Okay. So go by 1 hectare, 1 hectare, 1 hectare, because this is 2 hectare, 2 hectare. So if it is 1 hectare, just rough estimation. Okay. I can have a manifold, this 1 hectare, 1 hectare. So means you irrigate first 1 hectare, then irrigate the next one, then irrigate 1 hectare, next irrigate. So meaning that 4 times. But area is small, so then you need a less water. Less water means maybe half of this 1.34. So when 1.34, so this pipeline, your manifold will be smaller. Manifold will be smaller. Lateral will be small number here. Okay, but total lateral will be the same. Okay, manifold will be small. Okay, this pipe diameter will be small, so you can reduce some cost. The pump size also will be cost smaller because it is 1.34 now. Okay, but you operating 1 hectare, 1 hectare, 1 hectare, one by one. Okay, so you connect the system. Okay, then you have a gate bulb. Okay, you have to put the bulb. So you close, 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 supply one. Then this one finish, you close here, supply this. Okay, one by one. So this way you can also complete. Okay, another advantage for this in micro irrigation system. Normally within the manifold, this is the manifold. Within the manifold, you cannot change the crop. It should be the same crop. Okay, because different